Hello there, and welcome to Science for Sleep, where we take complicated ideas, slow them down, and give ourselves enough time to understand what scientists are actually discovering. Tonight, we're going to look at something that should have been fairly routine. The Sun entered another solar cycle. Scientists measured it. They compared it with previous cycles. They examined its magnetic field. They ran models. They gathered predictions from experts. And in 2019, an international panel organised by NOAA, NASA, and the International Space Environment Services reached a fairly cautious conclusion. Solar cycle 25 probably would not be especially dramatic. The previous cycle had been weak. Measurements of the Sun's polar magnetic field suggested that the next cycle might be similar. The official forecast expected the cycle to reach a smoothed sunspot number of about 115, with the peak arriving around July of 2025, although there was a fairly wide uncertainty in the timing. That sounded reasonable. Then the Sun started ignoring the forecast. Not immediately, of course. The Sun did not wake up one morning, look at the prediction, and decide to become difficult. Although, after following solar physics for long enough, you could perhaps be forgiven for imagining that it sometimes behaves that way. Solar activity began increasing as expected after the minimum between solar cycles 24 and 25. Sunspots returned. Flares became more common. Active regions appeared and disappeared as the Sun rotated. At first, there was nothing especially alarming about that. Then the numbers kept climbing. By the time the cycle reached its actual maximum, the official smoothed monthly sunspot number had reached about 161 in October 2024, rather than the predicted 115. On individual days during particularly active periods, the sunspot number went far higher than that, sometimes above 250. On August 8, 2024, preliminary daily estimates reached roughly 300. There is an important distinction here. A daily sunspot count should not be compared directly with the smoothed maximum used in long-term solar cycle forecasts. They are different measurements used for different purposes, so it would be misleading to say that the official maximum was literally twice the predicted value. But the basic problem remains. The forecast was substantially too low. Scientists had expected another relatively modest cycle. Instead, solar cycle 25 exceeded the previous cycle and became considerably stronger than the original prediction suggested. And while an inaccurate forecast might sound like an ordinary scientific inconvenience, this particular forecast concerns a star that can throw billions of tons of electrically charged material into space. Some of that material occasionally comes toward us. So, before we get comfortable with the idea that the Sun is simply a bright yellow circle that rises every morning and politely provides daylight, it may be worth remembering what it actually is. The Sun is a sphere of hot plasma, about 1.4 million kilometers across. It contains more than 99% of the mass in the entire solar system. Deep inside it, nuclear fusion converts hydrogen into helium, releasing the energy that eventually reaches Earth as light and heat. But the Sun is not only producing energy, it is also generating an enormous magnetic field, and that magnetic field is constantly changing. The visible surface of the Sun rotates, but not like a solid object. The equatorial regions rotate faster than the regions closer to the poles. Below the surface, hot electrically conducting plasma moves through different layers at different speeds and in different directions. When electrically conducting material moves, it can generate and reshape magnetic fields. In the Sun, this process becomes extremely complicated. Magnetic fields are stretched, twisted, transported, concentrated, broken apart and rearranged. In some places, intense magnetic fields rise through the visible surface and produce sunspots, those darker patches that can appear small in photographs but may be larger than Earth. A sunspot is not simply a stain on the Sun. It is evidence that something magnetic is happening below and around the surface. Regions with complicated magnetic fields can produce solar flares, sudden releases of electromagnetic radiation. They can also launch coronal mass ejections, or CMEs, enormous clouds of magnetized plasma that expand outward through the solar system. Most of the time, this activity is not aimed directly at Earth. Sometimes it is. In May 2024, one particularly active solar region produced a series of powerful flares and coronal mass ejections. At least 7 CMEs moved toward Earth during the event. Several arrived close together, and on May 10th and 11th, Earth experienced a G5 geomagnetic storm, the highest category on NOAA's geomagnetic storm scale. It was the first G5 storm since 2003. For millions of people, the most obvious result was beautiful. Auroras appeared far outside the places where people normally expect to see them. Skies turned green, purple, pink and red across unusually low latitudes. Phones came out. Photographs spread across the internet. People who had never travelled anywhere near the Arctic suddenly discovered that the Northern Lights were visiting them instead. For scientists and engineers, however, the event was more than an unusually good night for photography. A geomagnetic storm happens because material and magnetic fields from the Sun interact with Earth's magnetic environment. When the conditions are right, energy is transferred into the magnetosphere and upper atmosphere. That can affect technology. Satellite operations can become more difficult. Radio communication can be disrupted. GPS accuracy can degrade. Increased heating of Earth's upper atmosphere can increase drag on satellites in low Earth orbit. Electrical currents induced in long conductors can create problems for power systems. During the May 2024 storm, there were reported disruptions to navigation and communications, and some agricultural users of precision GPS systems had difficulty operating equipment accurately. The event did not cause a global technological disaster. That distinction matters. A G5 storm does not automatically mean civilization switches off and everyone spends Tuesday searching the garage for candles. But the event demonstrated how much modern life depends on systems that exist either in space or rely on signals travelling through an environment influenced by the Sun. And Solar Cycle 25 had already become much more active than the original prediction suggested, which leads to a rather uncomfortable question. How well do we actually understand the star sitting at the centre of our planetary system? You might think we would understand the Sun extremely well. After all, compared with other stars, it is very close. The nearest star beyond the Sun is more than 4 light-years away. The Sun is only about 8 light-minutes away. We can observe its surface in remarkable detail. We can measure its radiation across many wavelengths. We can map magnetic fields. We can study vibrations moving through its interior. We have spacecraft observing it continuously. NASA's Solar Dynamics Observatory has been watching the Sun since 2010. The Solar and Heliospheric Observatory has been operating since the 1990s. NASA's Parker Solar Probe has gone directly into the Sun's outer atmosphere, passing only about 3.8 million miles above the solar surface during its closest approaches. And Solar Orbiter, operated by the European Space Agency with NASA participation, has changed its orbit to give scientists something they had wanted for decades: clearer views of the Sun's polar regions from outside the flat plane in which Earth and most spacecraft travel. We have telescopes on the ground. We have telescopes in space. We have spacecraft near the Sun. We have decades of measurements. We have computer simulations running on machines that can perform extraordinary numbers of calculations every second. And the Sun can still surprise us. Perhaps that is worth thinking about tonight. Where are you listening from right now? And when you last saw the Sun, whether it was this morning, this afternoon, or through a window sometime during the day, did it look unusual to you? Probably not. That is one of the strange things about solar activity from the perspective of ordinary life. The Sun can be undergoing enormous magnetic changes while looking completely normal to us. Without specialised instruments, you would not see most solar flares. You would not notice magnetic fields becoming more complicated around an active region. You would not watch a coronal mass ejection expanding away from the sun at hundreds or even thousands of kilometers per second. You might be drinking coffee while several billion tons of solar plasma are moving through space. There is something pleasantly unfair about that. Your coffee has gone cold because you forgot about it for 7 minutes, while the nearest star has launched a magnetized cloud large enough to make planetary space weather forecasters reconsider their week. And this is why predicting solar activity matters. Scientists are not trying to predict the solar cycle because they enjoy counting dark spots on photographs, although there are people who genuinely enjoy doing that, and good for them. The larger goal is to understand how solar magnetism changes over time. Solar activity rises and falls in a cycle averaging about 11 years. Near solar minimum, the sun usually has fewer sunspots and fewer major eruptions. As the cycle develops, sunspots become more common. Magnetic activity becomes more complicated. Flares and CMEs occur more frequently. Near solar maximum, activity is generally highest. Then the cycle declines again. At some point during this process, the sun's global magnetic poles reverse. North becomes south. South becomes north. Then, during the following cycle, they eventually reverse again. The complete magnetic pattern therefore takes roughly 22 years. Scientists have records of sunspot activity stretching back centuries, and the basic cycle has been recognized for a very long time. But knowing that a cycle exists is not the same as being able to predict exactly what the next cycle will do. Imagine knowing that winter will eventually return but having difficulty predicting whether the next winter will be mild or whether you will spend January trying to remove ice from your car with something you found in a kitchen drawer. The calendar is not the hard part, the intensity is. And solar intensity matters because a stronger cycle generally means more opportunities for significant space weather. Not every large solar flare creates a major geomagnetic storm. Not every CME travels toward Earth. Even when one does, its effects depend on several details, including the orientation of its magnetic field when it reaches us. That makes predicting individual events difficult, but long-term solar cycle forecasts still matter because satellite operators, power grid planners, space agencies, communication companies, aviation organizations, and governments need some idea of the environment they may be dealing with years ahead. If you're planning a spacecraft mission that will operate for a decade, knowing whether the sun is expected to be unusually quiet or unusually active is useful. If you operate satellites in low Earth orbit, increased solar activity can change the density of the upper atmosphere and therefore change atmospheric drag. If you depend on precise radio signals travelling through the ionosphere, solar activity can change the conditions through which those signals move. For astronauts outside the protection of Earth's atmosphere and magnetic field, energetic particles from solar events can become a radiation hazard. So the forecast for solar cycle 25 was not a casual prediction. Scientists approached it using multiple methods. One of the most important clues was the strength of the magnetic field near the sun's poles during solar minimum. This method has a strong observational basis. The polar magnetic field near the end of one cycle appears to provide information about the strength of the next. A stronger polar field tends to be followed by a stronger solar cycle. A weaker polar field tends to be followed by a weaker one. You can think of the polar field as one measurement of the magnetic material available to help build the next cycle, although the real physics is considerably more complicated. Before solar cycle 25 began, measurements suggested polar magnetic fields similar in strength to those preceding solar cycle 24. Cycle 24 had been unusually weak by modern standards, so predicting something similar was reasonable. This was not scientists throwing a number at a wall and hoping it stayed there. It was a forecast built from observations, physical models, statistical techniques, and the behavior of earlier cycles. In 2019, the prediction panel considered dozens of forecasting approaches. The consensus settled near a maximum smoothed sunspot number of 115. Then the actual cycle climbed above it. By 2023, the mismatch had become difficult to ignore. NOAA released an updated experimental prediction, moving the expected maximum earlier and increasing the expected range. That improved forecast was based on the activity scientists were already observing. But by then, something important had already happened. The sun had shown that the original picture was incomplete. That does not mean solar science failed. Science does not work by producing one model and defending it forever. A failed prediction can be extremely useful because it tells researchers where their assumptions may be wrong. The interesting question is not simply, why did scientists get the number wrong? The interesting question is, which part of our understanding of the sun allowed the number to be wrong? And several possibilities are now receiving serious attention. One involves the polar magnetic fields themselves. The poles are extremely important to solar cycle prediction, but they are also difficult to observe from Earth. We view the sun from near its equatorial plane. That means the solar poles appear close to the edge of the visible disk, where magnetic measurements become more difficult. Imagine trying to determine exactly what is happening on top of a ball while your camera remains positioned near the side of it. You can gather information, you can build models, you can estimate what the top looks like, but you would probably still prefer to move the camera. That is one reason solar orbiters' changing viewpoint matters so much. In March 2025, the spacecraft reached an angle that allowed it to directly view the sun's south polar region more clearly than previous imaging spacecraft could from the usual orbital plane. As its orbit becomes more inclined over the coming years, scientists expect increasingly useful observations of regions that have traditionally been difficult to measure. And early observations have already shown a complicated magnetic environment near the poles during this phase of the cycle, with patches of different magnetic polarities mixed together. That matters because the polar fields are not just an interesting detail on a star. They may be one of the most important clues to what the next solar cycle will do. Another possibility is even more fundamental. Scientists may have been looking in the wrong part of the sun for the main machinery behind the solar cycle. For decades, many solar dynamo models placed enormous importance on a region called the tachocline. The tachocline lies deep inside the sun, around the boundary between the radiative interior and the convection zone above it. Because rotation changes dramatically across this region, it seemed like a natural place for magnetic fields to be stretched and organized. It became central to many explanations of the solar dynamo, the process that generates the sun's changing global magnetic field. But research published in 2024 presented evidence supporting a very different possibility. The process responsible for important features of the solar cycle may begin much closer to the surface, within roughly the outer 5 to 10% of the sun. That is not a small adjustment. Moving the effective location of the dynamo from deep near the base of the convection zone to a shallow layer near the surface changes the physical picture scientists are trying to model. It changes which flows matter most. It changes timescales. It changes how magnetic structures may form and migrate. And potentially it changes how solar activity should be predicted. Then there is another problem. Magnetic material moves across the sun. Large-scale flows can transport magnetic flux from lower latitudes toward the poles. The speed of this transport affects how the polar fields develop and therefore affects the magnetic conditions from which the next cycle emerges. If that material moves differently from what models assume, predictions can drift away from reality long before anyone notices the final sunspot number. There are also major questions about magnetic reconnection. This occurs when magnetic fields in plasma rearrange their structure and release stored energy. Reconnection is involved in solar flares. It is involved in eruptions, and observations from Parker Solar Probe are helping scientists investigate how reconnection may contribute to the solar wind itself. The solar wind is the continuous flow of charged particles leaving the sun and spreading through the solar system. Earth is inside that flow all the time, so are all the other planets. When the sun becomes active, the background solar wind can be joined by much more dramatic disturbances. Parker Solar Probe has flown directly through regions that previous spacecraft could only observe from a distance. measuring particles, magnetic fields, and plasma conditions near the Sun. Its observations have revealed a solar environment that is structured, variable, and often less tidy than simplified diagrams make it look, which is generally what happens when you finally visit a place you previously understood through drawings. The hotel brochure said, "quiet coastal atmosphere." You arrive and discover the seagulls have organised. The more closely we observe the Sun, the more details appear, and those details are not academic when they determine what reaches Earth. The May 2024 storm was powerful, but scientists know the Sun has produced larger events in the past. The famous Carrington event of 1859 occurred in a world without GPS satellites, global electrical grids, commercial aviation, widespread radio communication, cloud computing, or enormous constellations of spacecraft in low Earth orbit. Modern infrastructure gives us capabilities that 19th century society could hardly imagine. It also gives space weather many more things to interfere with. This does not mean an extreme solar storm would automatically destroy modern civilization. Claims like that are often exaggerated. Engineers design systems with space weather in mind. Forecasting centres monitor the Sun constantly. Satellite operators can take protective measures. Power grid operators can respond to warnings. But those protections work better when forecasts are good, and there are two very different forecasting problems. One is predicting the broad solar cycle years in advance. The other is predicting what a specific eruption will do after it happens. Solar Cycle 25 has reminded scientists that both problems contain major uncertainties. We underestimated the overall cycle. We still cannot reliably tell far in advance exactly which active region will produce a major eruption. Even when a coronal mass ejection is observed leaving the Sun, predicting its arrival time and magnetic configuration at Earth remains difficult. And the orientation of that magnetic field can make an enormous difference to the resulting geomagnetic storm. So there is an odd situation here. We live beside a star that we have observed longer and more carefully than any other star in the universe. We understand nuclear fusion. We understand many properties of plasma. We can measure the Sun's surface motion. We can reconstruct magnetic maps. We can launch spacecraft into its corona. And yet the machinery connecting the Sun's interior, its magnetic field, its surface activity, its corona, the solar wind and space weather at Earth still contains important gaps. Solar Cycle 25 made those gaps harder to ignore. It was forecast to resemble the weak cycle before it. Instead, the smoothed maximum reached about 161 in October 2024, well above the original prediction of 115. That difference between a predicted maximum of 115 and the much stronger activity that actually followed is where things start becoming interesting, because Solar Cycle 25 did not suddenly surprise scientists on one dramatic afternoon. The disagreement between prediction and reality developed gradually, month after month, until the original forecast became increasingly difficult to defend. To see how that happened, we need to go back to the end of 2019. At that point, the Sun was near solar minimum, the quiet period separating Solar Cycle 24 from Solar Cycle 25. Sunspots were scarce. The solar disk could go for long stretches looking almost completely blank. Large flares were uncommon. Major eruptions were less frequent. For people watching images from solar observatories, it was the closest the Sun gets to appearing relaxed. Of course, relaxed is a relative term when the object in question is a giant sphere of plasma with a core temperature of millions of degrees. But magnetically speaking, things were quiet. The new cycle was expected to begin slowly, rise over several years, reach its maximum around the middle of the decade, and then decline again. That basic shape was not controversial. What mattered was how high the activity would rise. The International Solar Cycle 25 prediction panel expected a relatively weak cycle, similar in strength to Solar Cycle 24. Their forecast called for a maximum smooth sunspot number of about 115, with the peak expected around July 2025. There was uncertainty around those numbers, because predicting the sun is not like checking a train timetable. The sun does not publish one. Solar cycles vary in length, shape and strength. Some rise quickly and decline slowly. Some have more than one apparent peak. Some produce a large number of sunspots without generating the most extreme storms. Others may appear less impressive overall, and still produce a particularly dangerous event. So the prediction of 115 was never meant to mean that the sun would reach exactly 115 sunspots on one particular day in July 2025, and then immediately begin calming down. Scientists use a smoothed sunspot number to describe the broad activity of the cycle. Daily sunspot counts jump around too much to be useful for identifying the true maximum. One day may be busy, another may be quieter, and large active regions rotate across the side of the sun visible from Earth and then disappear around the far side. The smoothing process reduces that short-term variation and makes the underlying cycle easier to see. This matters because during solar cycle 25, individual daily sunspot numbers sometimes became dramatically larger than the original predicted maximum. That produced some headlines suggesting the sun had reached nearly twice the expected level. In a daily sense, there were periods when counts really did climb that high, compared with the original forecast line. But the correct long-term comparison is less dramatic and still significant. The original panel expected a smoothed maximum near 115. The cycle later reached a smoothed level around 161 during its strongest period. So the cycle did not literally become twice as strong as forecast by that measurement. It exceeded the prediction by roughly 40%. For solar forecasting, that is not a tiny miss. Imagine a weather forecast calling for 10 inches of snow and receiving 14. You would probably consider the forecast substantially wrong, especially if you had planned your day around it. Now replace the snow with sunspots associated with magnetic regions capable of producing flares, radiation, and enormous eruptions of plasma, and the error becomes slightly more interesting. The first signs that the sun might not be following the expected path appeared surprisingly early. By 2022, NASA was already describing solar cycle 25 as exceeding predictions. The cycle had only recently begun, yet observed sunspot numbers were repeatedly running above the original forecast. At that stage, it was still possible that the difference would disappear. Solar cycles are messy. A strong early rise does not guarantee a strong maximum. Activity can accelerate, pause, surge again, or produce temporary spikes that make a cycle look more impressive than it eventually becomes. Scientists, therefore, had good reason not to abandon the original forecast simply because a few months looked unusual. But the stronger activity continued. More sunspots appeared. Active regions became larger and more complicated. Solar flares became increasingly common. The gap between the expected curve and the observed curve stopped looking like ordinary noise. By 2023, NOAA had enough evidence to make a major change. In October of that year, the Space Weather Prediction Center released an updated experimental forecast. Instead of expecting the maximum around July 2025, with a peak of 115, the revised prediction placed the likely maximum between January and October 2024, with a sunspot number between 137 and 173. That was a substantial correction. The sun was apparently moving toward maximum earlier than originally expected, and it was expected to become stronger. The interesting part is that the revised forecast turned out to be much closer to what happened. So this was not a situation where scientists remained confused while the sun became increasingly active and everyone simply stared at the monitors. Observations improved the prediction. Once the actual behaviour of the cycle became clear, forecasters adjusted. That is exactly what scientific forecasting is supposed to do. But it also means that the original forecast, the one based on conditions before the cycle developed, had failed to capture something important. Updating a prediction after the first several years of the cycle is useful. Predicting that behaviour before it happens is much harder, And that difference becomes very important when forecasts are being used to plan missions, design satellites, prepare electrical infrastructure, or estimate radiation conditions years into the future. By early 2024, the Sun was no longer behaving like the weak cycle many researchers had expected. Then May arrived. One active region became particularly difficult to ignore: NOAA, active region. 3664 grew into a huge and magnetically complicated sunspot group. It became several times wider than Earth and could even be seen without magnification under safe viewing conditions. Please do not test that by staring directly at the Sun. The Sun has already defeated the forecasting models. There's no need to let it defeat your retinas as well. Region 3664 produced repeated strong solar flares and launched several coronal mass ejections toward Earth. Between May 8th and May 9th, a series of eruptions sent magnetized clouds of solar material across interplanetary space. Some were moving at speeds approaching several million miles per hour. Because the eruptions occurred relatively close together, several of the resulting CMEs reached Earth in a compressed sequence. Rather than arriving as widely separated events, that became important. A single coronal mass ejection can disturb Earth's magnetic field. Several arriving in succession can produce a much more complicated interaction. Beginning on May 10th, Earth's magnetic environment responded strongly. The geomagnetic storm reached G5, the highest level on NOAA's 5-level scale. It was the first G5 storm recorded since 2003. For most people, the visible result was aurora. People who normally needed to travel far north to see the northern lights suddenly found them appearing much farther south. Auroral displays were reported across large parts of North America, Europe, and other regions where they are normally unusual. Photographs appeared from places that rarely feature in conversations about auroras. That was the attractive side of the storm. The less attractive side involved the systems that depend on stable conditions in near-Earth space. Geomagnetic storms can alter the ionosphere, the electrically charged region of the upper atmosphere through which many radio signals travel. GPS signals can become less accurate. High-frequency radio can be disrupted. Satellites may experience unusual electrical conditions, and when solar activity heats Earth's upper atmosphere, that atmosphere expands slightly, increasing drag on satellites in low Earth orbit. The May storm caused real operational problems. Some farmers using high-precision GPS systems reported difficulties with automated agricultural equipment. Satellite operators monitored changing atmospheric conditions. Communications and navigation systems experienced disturbances. Nothing resembling a global technological collapse occurred. Most people continued with their weekend. Lights stayed on, phones still worked. The internet remained available for everyone to upload several thousand photographs of the same green sky. But from the perspective of solar cycle forecasting, the event mattered. Here was a cycle expected to resemble the weak solar cycle 24, producing the strongest geomagnetic storm Earth had experienced in more than 20 years. There is an important caution, though. One extreme storm does not automatically prove that an entire solar cycle is extremely strong. Solar cycle strength and individual storm strength are related, but they are not the same thing. A moderate cycle can still produce a major eruption. A very active cycle may produce many eruptions that happen to miss Earth. Think of the solar cycle as changing the number of opportunities for the Sun to cause trouble, rather than determining exactly what will happen. A busier Sun produces more active regions, more flares, and generally more chances for significant space weather. But whether any particular eruption becomes important for Earth depends on where it occurs, what direction it travels, how fast it moves, and what its magnetic field looks like when it arrives. Still, Solar Cycle 25 was producing plenty of opportunities, and the activity did not stop after the May storm. On May 14th, the Sun released an X8.7 flare, which at that time was the strongest flare recorded during Solar Cycle 25. Solar flares are classified according to the strength of the X-rays detected near Earth. A-class flares are small, B-class flares are stronger, then comes C, M, and X. X-class events are the most intense category. Within the X category, the number gives additional information about strength. An X2 flare is stronger than an X1. An X8.7 flare is therefore not the Sun clearing its throat. It is a substantial release of electromagnetic energy. Then, in October 2024, another active region produced an X9.0 flare, becoming the strongest flare of the cycle up to that point. Again, a strong flare does not automatically mean a major geomagnetic storm. Flares and CMEs are different phenomena. A flare is an intense burst of electromagnetic radiation. That radiation travels at the speed of light, so effects on the sunlit side of Earth can begin within about 8 minutes. A coronal mass ejection is a large cloud of plasma and magnetic field physically moving through space. It takes much longer to reach Earth, usually many hours or sometimes several days. A flare can happen without an Earth-directed CME. A CME can produce different effects depending on its magnetic structure. This distinction is useful because solar cycle 25 was not simply producing more storms. It was producing more evidence that the Sun's magnetic activity had grown beyond the level anticipated before the cycle began. By October 2024, NASA and NOAA announced that the Sun had entered the solar maximum period. That wording is deliberate. Solar maximum is not necessarily one day. The Sun does not climb to a neat peak on Tuesday afternoon and become noticeably calmer on Wednesday. Maximum can be an extended period lasting months or longer. Sunspot activity may rise and fall several times. One hemisphere can become active before the other. Different indicators of solar activity may peak at different times. Researchers often have to wait until later, sometimes many months later, before identifying the exact maximum with confidence. This is another reason forecasting the solar cycle can feel a little like trying to identify the highest wave while you're still standing in the ocean. You can tell the water has become rough. You may strongly suspect that you've just seen the biggest wave, but you might prefer to wait before announcing that nothing larger is coming. The behaviour of solar cycle 25 also became interesting when compared with solar cycle 24. Cycle 24 was unusually weak. NOAA has described it as the weakest solar cycle in about a century, with a peak sunspot number around 116 by the measure used in its comparison. That weakness influenced expectations for cycle 25. Several forecasting approaches suggested another modest cycle, and there was a broader reason to take that possibility seriously. Solar activity had generally declined from the exceptionally strong cycles seen during much of the 20th century. Cycle 19, which peaked in the late 1950s, was enormous. Later cycles remained strong, but by the time cycle 24 arrived, sunspot activity had fallen significantly. Some researchers wondered whether the Sun might be entering a period of persistently reduced activity. Cycle 25 did not cooperate with that simple picture. It became stronger than cycle 24, not extraordinarily strong compared with the most powerful cycles in the historical record, but clearly stronger than many scientists expected. That distinction is worth keeping in mind. Solar cycle 25 is not the strongest solar cycle humans have ever observed. It has not approached the exceptional level of cycle 19. Even the updated NOAA forecast still place cycle 25 below the long-term average maximum of roughly 179 cited by the agency. So when we say the Sun became unexpectedly active, we are talking about unexpected activity relative to the forecast. The Sun did not suddenly enter a level of activity never seen before. The surprise was not that the Sun became impossibly violent. The surprise was that our best consensus prediction leaned weak, while the real cycle came in substantially stronger. That makes the forecasting problem more scientifically useful. If solar cycle 25 had produced some completely unprecedented form of behaviour, researchers could reasonably say that they had encountered a phenomenon no previous data could have prepared them for. But that is not what happened. The sun produced a recognizable solar cycle. Sunspots emerged in the usual way. Magnetic activity increased. The maximum arrived. Flares occurred. Coronal mass ejections occurred. The global magnetic field reversed as expected around maximum. Everything belonged to familiar solar physics, and yet the strength and timing were not captured correctly by the original consensus forecast. The ingredients were familiar. The recipe was wrong. That is much more interesting. It suggests that the problem may not lie in some exotic phenomenon that appears once every 1,000 years. It may lie in ordinary processes that happen during every solar cycle, but that we do not yet measure or model accurately enough. Consider what forecasters are trying to do. They observe conditions near solar minimum and attempt to infer the strength of activity several years later. They cannot see directly into every part of the sun. They cannot place magnetic sensors beneath the photosphere. They cannot watch the solar dynamo from the inside. Instead, they combine surface measurements, helioseismology, magnetic observations, historical relationships, physics-based models, and statistical methods. It is a little like trying to predict how strong a storm will become by looking at the ocean several years before the storm forms. Except the ocean is made of electrically conducting plasma. It is rotating differently at different latitudes. The magnetic field is being generated inside it. And the whole object contains enough mass to account for more than 99% of everything in the solar system. So perhaps we should allow the forecasters a difficult afternoon. The deeper concern is that solar cycle prediction is not merely about satisfying scientific curiosity. There are practical reasons to know how active the sun will be. When solar ultraviolet and X-ray output increases, Earth's upper atmosphere changes. During periods of high activity, the thermosphere becomes hotter and expands. Satellites orbiting a few hundred kilometers above Earth encounter more atmospheric particles. The drag is still tiny compared with what an aircraft experiences, but satellites are moving at roughly 17,000 miles per hour and remain in orbit for months or years. Small changes in drag accumulate. Their orbits can decay faster than expected. Operators may need to perform more corrections. Tracking becomes more difficult when many objects are affected at once. This issue has become more important because low Earth orbit is becoming crowded. Thousands of operational satellites now move through regions affected by solar activity. Commercial constellations have added spacecraft at a rate that would have seemed remarkable during previous solar cycles. A forecasting error therefore affects a very different space environment than it would have 30 years ago. Navigation is another concern. GPS does not work because your phone somehow knows where it is. Satellites transmit extremely precise timing signals. Your receiver compares signals from several satellites and calculates its position. Those signals pass through the ionosphere. Solar activity changes the ionosphere. Usually modern systems handle those changes well. During stronger disturbances, errors can increase. For someone using a phone to find a coffee shop, a temporary loss of precision may be annoying. For aircraft navigation, surveying, offshore operations, autonomous systems, or precision agriculture, it can matter considerably more. Radio communication has similar vulnerabilities. Strong flares can ionize parts of the upper atmosphere so quickly that high-frequency radio signals are absorbed. The result can be a radio blackout on the sunlit side of Earth. Airlines operating over polar regions, ships at sea, emergency services, military systems and other users may depend on radio channels affected by these events. Then there are electrical grids. Geomagnetic storms create changing magnetic conditions around Earth. According to basic electromagnetic physics, changing magnetic fields can induce electrical currents in conductors. Power transmission lines are very long conductors. Pipelines are conductors. Rail systems and other infrastructure can also experience induced currents. Under sufficiently extreme conditions, those currents can stress transformers and complicate grid operations. This is why space weather centers do not treat solar forecasting as a hobby for people with especially expensive telescopes. The forecasts feed into real decisions, and Solar Cycle 25 gave forecasters an unusually clear reminder that long-range predictions still contain significant uncertainty. The mismatch is even more noticeable when we look at how early it developed. By 2022, the cycle was already above expectations. By October 2023, NOAA formally revised the forecast. By May 2024, Earth experienced a G5 geomagnetic storm. By October 2024, the Sun was officially in its maximum period and had produced an X 9.0 flare. This was not one unexpected afternoon near the peak. The entire rise toward maximum was telling researchers that the initial estimate had missed something. There is also an important difference between saying that scientists failed to predict Solar Cycle 25 and saying that solar forecasting is useless. It is not useless. The original prediction correctly anticipated the general timing of the cycle and correctly recognized that Solar Cycle 25 would not resemble the most extreme cycles in the record. Later forecasts adjusted successfully as new observations arrived. Space weather forecasters detected the May 2024 eruptions and issued watches and warnings before the resulting storm reached Earth. The science worked well enough to provide meaningful preparation. The problem is more specific. The ability to predict the amplitude of a solar cycle before it begins remains limited. And if we struggle to determine whether an ordinary 11-year cycle will peak near 115 or substantially higher, there is an obvious question about our ability to anticipate the rare events that matter most. The largest solar storms do not politely wait for the strongest cycle. They do not require the sunspot number to reach a particular value. An active region with the right magnetic configuration can store enormous amounts of energy. A powerful CME can leave the Sun. If it is directed toward Earth, and if its magnetic field arrives in an orientation that couples efficiently with Earth's field, the resulting geomagnetic storm can become severe. Forecasting the broad cycle tells us about the background level of risk. It does not tell us exactly when the dangerous event will occur. That is why the stronger than expected behavior of Cycle 25 is more than an interesting correction to a graph. The original forecast was based on some of the best tools solar physicists had available. Something in those tools did not represent the Sun well enough. Perhaps measurements near the solar poles underestimated magnetic conditions that were already preparing a stronger cycle. Perhaps the relationship between polar fields and the next cycle is more complicated than current models assume. Perhaps magnetic material travels across the solar surface differently from the speeds built into those models. Perhaps the dynamo responsible for organizing the Sun's large-scale magnetism operates differently or in a different region than the standard picture suggests. Or perhaps several of these effects are involved at once. So where did that number of 115 actually come from? It is easy to look at Solar Cycle 25 now, after several years of stronger activity, and imagine that scientists simply underestimated the Sun. But before the cycle began, there were good reasons for expecting something quieter. The forecast was not based on one computer simulation, one telescope, or one scientist making an especially confident guess over lunch. Solar cycle forecasting uses several different approaches because the Sun does not give us one convenient measurement that tells us what it will be doing 5 years from now. Some methods look backward, others look at what the Sun is doing now, some attempt to model what is happening inside it, and some rely on magnetic clues left behind by the previous cycle. The first thing scientists need is one of the oldest measurements in solar astronomy, sunspots. People have been recording sunspots systematically for centuries. They are dark because the magnetic fields inside them suppress some of the normal movement of hot plasma from below, making those regions cooler than the surrounding photosphere. Cooler in this case still means several thousand degrees, so there is no need to feel sorry for them. Sunspots are useful because they provide a visible sign of solar magnetism. Near solar minimum, there may be days or even long periods with very few sunspots, As activity rises, more appear. Near solar maximum, the visible surface can become crowded with active regions. This relationship gives scientists a basic way of describing the solar cycle. Count the sunspots over time, smooth out the short-term fluctuations, and a broad rise and fall begins to appear. That sounds simple, until you actually try to use it to predict the future. A solar cycle lasts roughly 11 years, but 11 years is an average, not a schedule. Some cycles are shorter, others are longer, some climb rapidly, others take their time. Some produce one broad maximum, others appear to peak, weaken, and then rise again because activity in the sun's northern and southern hemispheres does not always develop at exactly the same rate. Even deciding when one solar cycle has officially begun requires patience. The cycles overlap. As an old cycle fades, sunspots belonging to the new cycle begin appearing, while some spots from the previous cycle are still present. Fortunately, those spots carry magnetic information that helps scientists tell the generations apart. Sunspot groups usually contain regions of opposite magnetic polarity. The orientation of those polarities follows a pattern that changes from one solar cycle to the next. New cycle sunspots also tend to appear at higher solar latitudes before gradually emerging closer to the equator as the cycle progresses. So researchers are not simply counting spots. They're examining where they appear, how their magnetic polarities are arranged, how frequently they emerge, and how those patterns change with time. When solar cycle 25 began, scientists could not immediately announce the exact date of minimum. That could only be determined later. Solar minimum is the point when the smooth sunspot number reaches its lowest level, and naturally you cannot know that you've reached the lowest point until the numbers begin rising again. It is a little like finding the cheapest petrol station on a long drive. You only discover with complete confidence that the last one was the cheapest after passing 3 more and realizing you should have stopped 20 miles ago. In September 2020, NASA and NOAA announced that the previous solar minimum had occurred in December 2019. That date marked the beginning of solar cycle 25, but the prediction itself had already been developed. In March 2019, 12 experts met as part of the Solar Cycle 25 Prediction Panel, an international effort sponsored by NOAA and NASA, with participation through the International Space Environment Services. They were not handed one model and asked whether they liked it. According to NASA, they considered roughly 60 forecasts produced using different methods. Those methods did not all agree. That is normal. One model might examine patterns in previous sunspot cycles, another might use measurements of the sun's magnetic field, another might model how magnetic material moves across the solar surface, another might use geomagnetic activity recorded at Earth as a clue to changes on the sun. Others use radio emissions, statistical relationships, dynamo simulations, or machine learning methods. Each approach is trying to extract information from a system we cannot directly inspect. We can observe the sun's visible surface in extraordinary detail. We can measure its magnetic field there. We can use helioseismology to infer motions below the surface by studying waves passing through the sun. But we cannot lower an instrument into the solar convection zone and ask the plasma what it plans to do in 2027. This creates an unusual forecasting problem. Scientists know that the magnetic cycle is being generated by motions inside the sun, but many of the details of that machinery must be inferred indirectly. Imagine trying to predict the behavior of an engine while standing outside a closed garage. You can hear it. You can measure the vibration of the walls. You can smell the exhaust. You can watch the wheels turn when the vehicle eventually comes outside. From all of that, you can learn a remarkable amount. But you might still appreciate someone opening the bonnet. Solar physicists do not currently have that option, so they look for precursors. A precursor is something measurable now that has shown a useful relationship with solar activity later, and among the available precursors, one had become especially important by the time researchers were preparing the Cycle 25 prediction. The magnetic fields at the sun's poles. The relationship had worked surprisingly well. When the polar fields near solar minimum are strong, the following cycle tends to be strong. When the polar fields are weak, the next cycle tends to be weak. Scientists therefore use the polar field near minimum somewhat like a farmer might use stored water at the end of one season to estimate what will be available for the next. The analogy is not exact because solar magnetism is considerably less cooperative than a reservoir, but the basic idea is useful. The magnetic field accumulated near the poles at the end of one cycle helps establish the conditions from which the next cycle develops, and before solar cycle 25 began, the polar fields did not look particularly impressive. They appeared roughly similar in strength to those preceding solar cycle 24. That was important because cycle 24 had been weak. Its peak was well below the long-term average. If the polar field precursor was reliable, and the polar fields before cycle 25 resembled those before cycle 24, then expecting another relatively weak cycle made sense. NASA described the polar field model in 2020 as one of the approaches that had performed especially well in recent cycles. At solar minimum, the poles act as a useful indicator of the strength of the cycle that follows. This did not mean every prediction gave exactly the same number. One NASA-supported precursor study, for example, used a combination of polar magnetic field measurements and the sun's radio emission at a wavelength of 10.7 centimeters. That radio measurement is known as F10.7. It has been recorded for decades and tracks solar activity remarkably well. The study estimated that cycle 25 could reach a smooth sunspot number around 135, with a fairly large uncertainty of plus or minus 25. That still suggested a cycle broadly comparable to cycle 24, rather than a return to the enormous cycles of the mid-20th century. Other methods produced different answers. Some were lower, some were higher. This range is exactly why the prediction panel existed. Its job was not to choose whichever model had the nicest graph. The panel compared the available forecasts, examined the assumptions behind them, discussed which methods had performed well before, and tried to identify where the strongest agreement existed. NASA later described the process as similar to hurricane forecasting. Meteorologists do not normally trust one model completely when a major storm is approaching. They compare many models. If several independent methods begin converging on a similar track, confidence increases. Solar scientists were trying to do something similar, except their hurricane was about 1.4 million kilometers wide, and the forecast extended several years into the future. Eventually, the panel reached a consensus. Solar cycle 25 would probably resemble solar cycle 24. The expected smoothed maximum sunspot number was 115. The expected peak was around July 2025. There were uncertainty ranges around both values. The panel did not claim that the maximum would be exactly 115, or that the sun would reach it on one specific day. The forecast range placed the likely maximum between roughly 105 and 125, while the timing range extended from late 2024 into early 2026. NOAA later summarized the 2019 panel result as a prediction of 115, with an expected peak around July 2025. At the time, that looked reasonable. Cycle 24 had been the weakest cycle in about a century by NOAA's comparison. The polar field suggested something similar. Several precursor methods pointed toward moderate or weak activity. And for a while, nothing happened that required anyone to throw the forecast into the bin. The sun was emerging from minimum. New cycle sunspots appeared. Activity gradually increased. Exactly what a new solar cycle was supposed to do. But forecasts are not really tested when everything is quiet. They are tested when the observed curve begins separating from the predicted one, and that started happening sooner than many people expected. During 2021, sunspot activity showed signs of strengthening. There were months when the observed numbers moved above the original prediction. 1 month above the forecast is not especially meaningful. Neither is one unusually active week. Solar activity is noisy. A large active region can rotate into view and suddenly increase the sunspot count. 2 weeks later, it may rotate around the far side, and the visible sun can look much quieter. That is why scientists use smoothed values when comparing the long-term cycle with predictions. The daily number is weather. The smooth progression is closer to climate. Not literally, of course. Please do not put that analogy into a climate model. But the distinction is similar. One unusually warm afternoon does not tell you the average temperature of a year. One enormous sunspot group does not tell you the final amplitude of a solar cycle. Researchers therefore watched. The activity remained stronger. Then they watched some more. It still remained stronger. By July 2022, NASA was publicly describing solar cycle 25 as exceeding predictions. The sun had been more active than the consensus forecast expected, and the difference had persisted long enough to become scientifically interesting. At this point, something important happened to the original forecast. It did not instantly become worthless. Scientists could still compare the ongoing cycle with it. The expected timing remained useful. The forecast gave researchers a baseline for understanding how unusual the actual behaviour was. But confidence in the predicted amplitude was weakening. The sun was climbing faster and higher than the original trajectory. One explanation might have been that cycle 25 was simply rising quickly, but would stop early. Solar cycles do not all follow identical shapes. A rapid early increase does not guarantee a high final maximum. Perhaps activity would level off. Perhaps the cycle would settle back toward the predicted range. Perhaps the original model would look much better after another year. Then another year arrived. The activity did not return obediently to the old curve. By 2023, NOAA's Space Weather Prediction Center had a practical problem. Its customers use long-range solar cycle forecasts for real planning. Spacecraft designers need estimates of future solar conditions. Satellite operators need to anticipate atmospheric drag. Mission planners need estimates of radiation and space weather conditions. Various engineering models use quantities such as sunspot number, F10.7 radio flux, and geomagnetic activity to estimate the environment spacecraft may experience. A forecast that has clearly drifted away from observations cannot remain useful simply because everyone worked very hard on it in 2019. The sun is not known for respecting committee decisions. In October 2023, NOAA announced that the 2019 panel prediction was no longer reliable enough for those needs. That sentence is worth pausing over. It was not a newspaper columnist declaring that scientists had been wrong. It was NOAA's own Space Weather Prediction Center saying that the forecast needed to change. The new experimental prediction expected the maximum to arrive earlier, between January and October 2024. It also raised the expected maximum sunspot number to somewhere between 137 and 173. Instead of another peak around 115, in July 2025, NOAA was now preparing for a stronger and earlier maximum. The new system also changed something about the forecasting process itself. Rather than producing one prediction before the cycle and leaving it unchanged, the experimental forecast would be updated monthly as new sunspot observations arrived. In other words, instead of asking the model to tell us in 2019 exactly what the sun would be doing many years later, NOAA began allowing current observations to continuously correct the forecast. Mark Mesh, solar cycle lead at NOAA's Space Weather Prediction Center, described this as a significant change, noting that the 2019 forecast had not been updated since its original release and was no longer reliable enough for users who plan operations years ahead. There is an important difference between these two kinds of prediction. Suppose you're asked today to predict the temperature on a particular day 4 years from now. That is extremely difficult. Now suppose that when the day finally arrives, you're allowed to update your forecast every hour using satellite measurements, weather stations, and radar. Naturally, the second prediction should become much better. Solar cycle forecasting works in a somewhat similar way. Before a cycle begins, scientists are attempting a true long-range forecast. They have measurements from the previous cycle, they have precursor signals, they have theoretical models, they have statistics. But they do not yet have several years of observation showing how quickly the new cycle is actually developing. Once the cycle is underway, those observations become powerful information. If sunspot numbers have been above the predicted trajectory for 2 years, the model no longer has to guess whether the new cycle might rise faster. It already has. The updated NOAA forecast was therefore able to correct itself using evidence that did not exist when the original prediction was made, and that is useful operationally. Scientifically, though, the more interesting question remains the original one. Why did the forecasts made before the cycle began come in too low? There were some predictions that anticipated stronger activity. The scientific community was never unanimous. One research team led by Scott McIntosh had published a substantially stronger forecast based on a different way of analysing the timing and termination of magnetic activity bands associated with successive solar cycles. NASA pointed out in 2022 that the developing cycle 25 was looking more consistent with that stronger prediction than with the official panel forecast. That is worth remembering because science rarely gives us a tidy story in which everyone predicts one thing and nature reveals another. Usually there are competing ideas. Some predictions succeed, some fail. Then researchers try to understand why. Simply identifying the winning forecast afterwards is not enough. A method has to work repeatedly. If 20 people independently predict the result of a coin toss using 20 different theories, someone will probably be correct. That does not necessarily mean that person has discovered a new law of coin physics. The difficult part is determining whether the correct prediction succeeded because its underlying model represented the sun more accurately, or because the answer happened to land close to reality this time. Solar scientists have seen this problem before. Cycle 24 also produced widely different predictions before it began. Some methods expected a strong cycle, others predicted a weak one. The weak predictions turned out to be closer. That experience strengthened interest in polar magnetic field precursors because the weak polar fields before cycle 24 had pointed toward a weak cycle. So when the polar fields before cycle 25 again appeared modest, the reasoning seemed even more persuasive. This is how scientific confidence develops. A method predicts something, nature tests it, the method succeeds, researchers use it again. If it succeeds repeatedly, confidence increases. But every successful prediction also creates an opportunity for an uncomfortable assumption to hide inside the model. Maybe the relationship works only under certain conditions. Maybe the measurements contain a bias. Maybe a process that happened to behave consistently across several cycles changes during the next one. And with the sun, researchers have a limited number of well-observed cycles available for testing modern magnetic models. Direct high-quality measurements of the global solar magnetic field cover only a small fraction of the centuries-long sunspot record. Satellites have observed the sun continuously for only a few decades. That is a long time for a human research project. It is not a long time when the phenomenon you are studying repeats roughly once every 11 years. A scientist can spend an entire career and watch only a handful of complete solar cycles. Imagine trying to understand the climate of Earth after observing 6 winters. You might learn a great deal. You would also be rather brave to announce that winter number 7 had no surprises left. This problem becomes even more serious for the solar dynamo. The dynamo is the process by which movements of electrically conducting plasma generate and reorganize the sun's magnetic field. Every solar cycle prediction ultimately depends, directly or indirectly, on the behavior of this magnetic system. Even statistical models are learning patterns created by the dynamo. Polar field precursor models are measuring one stage of the dynamo process. Surface flux transport models try to follow magnetic material as flows carry it around the sun. Physics-based dynamo models attempt to reproduce the underlying mechanisms that generate the cycle, and those methods can disagree because scientists still debate important details of how the dynamo works. Where exactly is the magnetic field being generated and amplified? How much of the cycle is controlled deep inside the convection zone? How important are processes near the surface? How fast does magnetic flux move toward the poles? How deeply do the large circulation patterns penetrate? How much randomness is introduced when active regions emerge? How strongly does the magnetic configuration of one cycle determine the next? These are not tiny details being added to an otherwise completed picture. They influence the forecast itself. Surface flux transport models provide a good example. When sunspot groups emerge, they bring magnetic flux to the surface. As those regions decay, their magnetic material spreads. Several processes then move that flux around. The sun rotates. Small convective motions disperse magnetic fields, and a large-scale circulation known as meridional flow carries material generally from lower latitudes toward the poles near the surface. This transport helps build the polar magnetic fields. Those polar fields then become one of the most valuable predictors of the next cycle. So the forecast contains a chain of events. Active regions emerge, their magnetic flux disperses, surface flows transport it, the polar field develops, scientists measure that polar field, the measurement becomes a predictor of the next cycle. If any important part of that chain is misunderstood, the forecast can inherit the error. Perhaps the transport speed is wrong. Perhaps active regions contribute magnetic flux differently than the model assumes. Perhaps the polar field is stronger than our viewing geometry allows us to measure accurately. Perhaps the connection between the polar field and the deeper magnetic field that produces future sunspots is not as simple as expected. Solar Cycle 25 turned these possibilities from technical concerns into something much harder to ignore. The polar field precursor had been one of the strongest reasons to expect a weak cycle. The cycle was not as weak as expected. So either the clue was interpreted incorrectly, the clue itself was measured imperfectly, or the physical relationship connecting that clue to future activity contains something the models are missing. And the poles are a particularly suspicious place to start looking. From Earth, we do not see them well. Earth orbits the Sun close to its equatorial plane. Most solar observatories have historically observed from roughly the same broad viewing geometry. When scientists try to measure the magnetic field near the solar poles, they are looking at regions close to the edge of the visible disk. The geometry makes the measurement difficult. Magnetic field instruments often measure the component of the field along the observer's line of sight, near the center of the solar disk that can provide a relatively straightforward view of magnetic structures. Near the poles, the viewing angle becomes awkward. It is the difference between looking directly down at a football pitch and trying to work out what is happening while standing almost level with the grass. You can still gather information, you can make corrections, you can build maps, but uncertainty grows. For decades, solar physicists knew this. They did not assume polar measurements were perfect. They developed methods to estimate the field. They used changes in Earth's viewing angle over the year. They combined observations over time. They built models, and those techniques produced useful results. But Solar Cycle 25 raised the obvious possibility that useful may not be the same as precise enough. If the polar magnetic field was one of the most trusted ingredients in the 2019 forecast, and that forecast substantially underestimated the developing cycle, then perhaps the first place to investigate is the ingredient that carried so much weight. Because the question is no longer simply how scientists forecast the sun. The question becomes whether the magnetic signal they believed they were measuring at the poles was really telling them the whole story. Scientists trust the sun's polar magnetic fields because, historically, they have been one of the best clues to the strength of the next solar cycle. At the same time, the polar regions are among the parts of the sun we have had the most difficulty observing properly. That combination should make anyone a little cautious. It is rather like trying to predict next year's harvest using the temperature inside a greenhouse, while the thermometer is mounted behind a curtain at an inconvenient angle. The measurement can still be useful. You would simply prefer a better thermometer. To understand why the polar magnetic fields matter so much, we need to briefly follow what happens to magnetic material during an ordinary solar cycle. Around solar maximum, the visible surface becomes busy with active regions and sunspots. These active regions contain strong magnetic fields. A typical sunspot group does not simply contain one magnetic polarity. It usually contains areas where magnetic field emerges from the surface and other areas where it returns. Those magnetic regions are gradually broken apart by motions in the solar plasma. The magnetic flux does not disappear, it spreads across the surface. Some of it cancels against magnetic flux of the opposite polarity. Some remains. Large-scale flows on the Sun then transport part of that surviving magnetic material toward the poles. This transport takes years. By the time the Sun approaches minimum, the magnetic fields accumulated around the north and south poles become relatively organized, and those fields seem to contain information about what the next cycle will become. This is why solar physicists sometimes describe the polar field as the seed of the next cycle. It is not a literal seed, of course. There is no small magnetic sunflower waiting at the North Pole. The idea is that the large-scale magnetic configuration near solar minimum becomes part of the process that produces the stronger magnetic fields responsible for future sunspots. If the polar field is strong around minimum, the next sunspot cycle generally tends to be strong. If it is weak, the following cycle tends to be weaker. This relationship became especially convincing after solar cycle 24. Before that cycle began, the Sun's polar fields were unusually weak. Researchers using polar field precursor methods predicted that the next cycle would also be weak, and that is what happened. Solar cycle 24 became the weakest solar cycle in roughly a century by the measures used in NASA and NOAA comparisons. So when scientists approached the minimum before cycle 25, they naturally looked at the poles again. The polar fields appeared to be roughly comparable to those observed before cycle 24. The conclusion seemed fairly straightforward. If similar polar fields had produced a weak cycle 24, similar fields might produce a similar cycle 25. That reasoning played an important role in the official prediction. NASA described the polar field method before cycle 25 as one of the most successful forecasting approaches used in recent cycles. The basic relationship was simple enough. Stronger polar fields around minimum tend to precede stronger cycles, while weaker polar fields tend to precede weaker ones. And then cycle 25 became considerably stronger than that expectation. So what happened? One possibility is that the polar field itself was not telling us quite what we thought it was telling us. Another possibility is that we did not measure it accurately enough. And a third possibility is that the polar measurement was perfectly reasonable, but the physical relationship between polar fields and future sunspots is more complicated than the models assumed. At the moment, it would be too strong to say that scientists have proven the original forecast failed simply because instruments underestimated the polar fields. That is an attractive explanation, and measurement difficulties are very real, but solar cycle 25 does not give us a receipt from the Sun saying, "Forecast error caused by magnetometer. Please contact customer service." Researchers are still trying to separate several possible effects. The measurement problem, however, is worth examining because it has existed for as long as we have been trying to map the Sun's poles. Most observations of the Sun are made from near the plane in which Earth orbits. This plane is called the ecliptic. Earth, most planets, and most Sun-observing spacecraft remain fairly close to it. From that position, we see the Sun mainly from the side. We get an excellent view of the regions near the centre of the visible solar disk. The poles are another matter. They sit near the upper and lower edges. Try an experiment with any ball nearby. A tennis ball will do. A globe is even better. Hold it directly in front of your face. The middle of the ball is easy to see. Now try to examine a small area exactly at the top, while keeping your eyes level with the centre. You can see toward the top. You may see features close to the pole, but the exact polar region is heavily foreshortened. Features appear compressed. Part of the surface curves away from you. The sun creates the same basic geometric problem. And because magnetic instruments are trying to measure not just what the surface looks like, but what the magnetic field is doing, the viewing angle matters enormously. A common solar magnetic map is called a magnetogram. Magnetograms can be produced by measuring subtle changes in sunlight caused by magnetic fields in the solar atmosphere. One of the most important effects used for this is the Zeeman effect. Magnetic fields alter the energy states of atoms, producing small changes in spectral lines. By measuring the polarization and splitting of those lines, instruments can infer magnetic properties of the region where the light originated. NASA's Helioseismic and Magnetic Imager, or HMI, aboard the Solar Dynamics Observatory routinely produces full-disk measurements of the photospheric magnetic field. One standard HMI product measures the component of the magnetic field pointing along the instrument's line of sight. That phrase, line of sight, is where things become troublesome. Suppose a magnetic field points almost directly toward your instrument. Measuring the part aligned with your line of sight is relatively straightforward. Now rotate that same field until it is almost sideways from your perspective. The component pointing toward you becomes much smaller, even though the actual magnetic field is not weakened. Near the solar poles, geometry makes those interpretations more difficult. Scientists can apply corrections. They can combine multiple observations. They can estimate the likely direction of the field. They can use more sophisticated vector magnetograms that attempt to recover additional information. But every correction depends on assumptions, calibration, noise levels, spatial resolution, and viewing angle. And the higher solar latitudes are not merely awkward. For part of the year, some of the region nearest one pole can effectively disappear from useful direct observation. The Sun's rotation axis is tilted by about 7.25 degrees relative to Earth's orbital plane. As Earth moves through its orbit, our view alternately favours the northern and southern solar hemispheres. At one time of year, we see a little more of the north. Several months later, we see a little more of the south. The result is that the size of the poorly observed region around each pole changes over the year. NEA visualizations of solar magnetic maps explicitly include these polar gaps, where measurements must be supplemented with modelled or estimated values, because the geometry prevents satisfactory direct coverage. That is a rather important detail when the quantity you're trying to measure is being used to predict solar activity years into the future. We have spent decades saying, quite reasonably, that the polar magnetic field is one of our best predictors, but until recently, we had never had a modern imaging solar observatory rise far enough above or below the ecliptic to look directly into those polar regions. We were predicting the future using a part of the sun we had never properly looked down upon. This does not mean the old measurements were bad. They were often extremely good considering the geometry. Observatories such as the Wilcox Solar Observatory have maintained polar field records since the 1970s. Space missions have improved magnetic observations enormously. Researchers have developed correction methods and have compared instruments to ensure that measurements remain useful over decades. Those records allowed the precursor relationship to be discovered in the first place. Without them, we would know much less. The issue is that good enough to identify a relationship and good enough to predict the exact amplitude of the next solar cycle are not necessarily the same standard. Imagine weighing suitcases at an airport using a scale that is usually accurate within a kilogram. If all you need to know is whether one suitcase is much heavier than another, the scale works beautifully. If the airline charges you $200 when the bag exceeds 23 kilograms by a few hundred grams, you suddenly become very interested in calibration. Solar cycle 25 may be doing something similar to our confidence in polar measurements. The original forecast did not miss, because scientists thought the poles were completely inactive. The measured field suggested a cycle roughly comparable to cycle 24. Several independent polar field predictions produced values in the general neighbourhood of the official forecast rather than predicting an enormous cycle. For example, One analysis using Wilcox Observatory polar field measurements later estimated a cycle 25 amplitude near 125, while other precursor-based work also expected something broadly similar to, or slightly stronger than, cycle 24. Those estimates were not absurd. They were simply too low compared with what cycle 25 eventually produced. Now suppose the true high-latitude magnetic field was somewhat stronger or structured differently from the quantity our usual observations captured. That difference could influence a forecast based on the assumption that the measured polar field is an accurate representation of the magnetic seed for the next cycle. But there is another complication. What do we actually mean when we say the polar field? The Sun does not have two perfectly smooth magnetic caps painted onto its surface. At large scales, we can describe a dominant polarity near each pole. At smaller scales, the surface contains many magnetic structures. Flux is concentrated into patches. Different features emerge, move, cancel, and reorganize. The field can have radial, horizontal, and more complicated components. A single average number inevitably simplifies all of that structure. During some parts of the cycle, the simplification works reasonably well. Around solar minimum, one polarity tends to dominate each pole. Near maximum, everything becomes much more complicated because the Sun's global magnetic field is reversing. Old polar flux disappears. New flux arrives. North and south polarities can coexist in the same polar region, while the reversal is underway. This matters enormously, because that reversal is how the Sun prepares the polar field that will eventually become the precursor for the following cycle. To predict one solar cycle well, researchers need to understand not only the field at minimum, but how it got there. That brings us back to the magnetic material travelling from active latitudes toward the poles. Sunspots usually appear in pairs or groups with opposite polarities. Because those groups are often tilted relative to the solar equator, one polarity tends to sit slightly closer to the pole than the other. When the active region decays, this small difference matters. Magnetic material from one side of the region has a better chance of being transported poleward. Over many active regions and several years, the accumulated effect helps cancel the old polar field and construct the new one. A slight change in the average tilt of sunspot groups can therefore change how much magnetic flux reaches the poles. A few unusually large or strangely tilted active regions can matter more than you might expect. The speed of the surface flow matters too. If magnetic material moves toward the poles faster than a model assumes, the timing and amount of cancellation can change. If the flow slows down, the result changes again. Diffusion caused by smaller convective motions complicates the transport further. So even if a magnetograph measures the existing polar field perfectly, a prediction can still fail because the model does not correctly represent the process that built that field or the way it connects to the next cycle. This is why describing cycle 25 as a simple case of scientists misread the poles needs a little care. We may indeed have been missing information at the poles, but the missing information may involve more than field strength. It may involve structure, transport, viewing geometry, small-scale magnetic features, differences between the northern and southern hemispheres, or the possibility that the polar field is a useful predictor without being the direct controlling mechanism researchers sometimes imagine. And then, in 2025, we finally changed the viewing angle. Solar Orbiter had been launched in 2020 as a joint ESA-led mission with NASA participation. For its first years, it remained relatively close to the familiar orbital plane. That was always going to change. Using repeated gravitational encounters with Venus, Solar Orbiter gradually altered the inclination of its orbit. By March 2025, the spacecraft had moved far enough below the solar equator to view the Sun from an angle reaching about 17 degrees. That may not sound particularly dramatic. 17 degrees will not impress anyone designing a ski slope. For solar astronomy, it was revolutionary. For the first time, a sun-watching spacecraft equipped with modern imaging instruments was obtaining clear views of the solar poles from outside the ecliptic plane. Earlier missions had travelled over the polar regions. The Ulysses spacecraft, launched in 1990, passed over the Sun's high latitudes and made important measurements of particles and magnetic conditions. But Ulysses did not carry an imaging telescope capable of producing the kinds of detailed magnetic maps Solar Orbiter can create. Solar Orbiter brought cameras and magnetic mapping instruments into a viewing geometry solar physicists had wanted for decades. ESA released the mission's first clear polar views in June 2025, based on observations made from roughly 15 to 17 degrees below the solar equator during March. The timing was especially useful because the Sun was around its maximum period. That meant Solar Orbiter was not looking at a simple settled polar field. It was watching the magnetic reversal, and what it saw was messy. The Polarimetric and Helioseismic Imager, or PHI, produced maps showing both magnetic polarities reaching into the south polar region. Instead of one clean magnetic sign covering the pole, the map contained patches of positive and negative field. This was not evidence that something had gone wrong with the Sun. Mixed polarity is expected during the reversal around maximum. The old global field is being replaced. What mattered was that scientists could now observe the process from an angle that had never previously been available to an imaging spacecraft. ESA described the poles during this phase as magnetically mixed, with both north and south polarities present, and noted that understanding exactly how one polarity eventually builds up and dominates remains an open problem. That last part is especially important. We use the final polar field as a predictor, but we are still learning how that final polar field is assembled. It is a little like being very good at predicting tomorrow's bread quality from the dough just before it goes into the oven, while admitting that several parts of the recipe remain uncertain. Useful? Absolutely. Complete? Not quite. Solar Orbiter will improve its polar view further. Its orbit is designed to become increasingly inclined, allowing future observations from higher solar latitudes. That gives scientists the opportunity to follow the polar fields as cycle 25 declines toward its eventual minimum. They can watch magnetic flux arrive. They can measure how rapidly the dominant polarity becomes established. They can compare those measurements with the estimates made from near-Earth instruments, and they can determine whether the polar field that looks one way from the ecliptic appears significantly different when viewed more directly. This is where the question of underestimation can finally become testable in a much stronger way. Suppose Earth-based measurements systematically miss some high-latitude field because of projection effects. Solar Orbiter should help quantify that. Suppose the average strength is correct but important small-scale structure is missing. Solar Orbiter can investigate that too. Suppose the polar fields measured from Earth turn out to be remarkably accurate after all. That would be equally useful, because it would push attention away from the instruments and toward the models connecting those measurements to the next cycle. Science becomes easier when you can eliminate suspects. The poles are not only important for the next batch of sunspots, they also influence the magnetic structure extending far beyond the visible surface. Near solar minimum, large regions around the poles often contain open magnetic field lines. Open does not mean the magnetic field simply ends. Magnetic field lines do not have loose ends floating around. It means the field extends outward into the heliosphere rather than closing back onto the nearby solar surface. Charged particles can escape along these magnetic structures and contribute to the solar wind. The polar regions are therefore connected to the vast magnetic environment filling the solar system. NASA has pointed out that the polar field, combined with the outward flow of the solar wind, affects magnetic structures extending toward the regions where Earth and other planets orbit. So when the poles change, the consequences are not confined to two small patches at the top and bottom of a solar map. They are part of the global reorganization of the Sun's magnetic field. During maximum, that organization becomes complicated. The large-scale field weakens and reverses, coronal holes move, the solar wind changes, active regions appear across broad bands of latitude. Eventually, as activity declines, a clearer dipole-like magnetic structure develops again. By the next minimum, researchers will measure the polar fields and immediately begin using them to discuss solar cycle 26. And this time, they may have observations from an angle no previous prediction panel had. That could improve forecasting. It may also create new problems. Better observations have an annoying habit of revealing that the simple variable you were measuring was made of 6 variables you had not noticed. You buy a better microscope expecting a clearer answer and discover an entire ecosystem living on your desk. The same thing may happen with polar magnetism. A single number representing average polar field strength is convenient. The actual polar region may turn out to contain patterns of flux, flows, emergence, cancellation, and small-scale structure that must be represented more carefully if we want truly reliable predictions. Solar cycle 25 has already shown why that matters. The precursor method had good historical evidence behind it. The polar measurements suggested a modest cycle. The consensus forecast followed that evidence. The cycle came in stronger. That does not invalidate polar fields as predictors. They remain one of the most valuable pieces of information solar physicists have. Instead, it tells us that a strong correlation is not the same as a complete physical explanation. The distinction can be easy to miss. Suppose every morning you notice that your neighbour opens the garage door 5 minutes before their car leaves. After several years, you become very good at predicting when the car will appear. Garage door opens, 5 minutes later, car. Excellent model. Then one morning, the garage opens and no car leaves. The prediction has failed. Perhaps the car has a flat tyre. Perhaps someone opened the door to take out a bicycle. Perhaps the driver changed their routine. The old relationship was real. It was useful. But you never actually understood why the garage door was opening. Solar physicists understand considerably more about polar magnetism than we understand about our imaginary neighbour, but the warning is similar. A predictor can work repeatedly without containing every piece of the underlying mechanism. The polar fields tell us something important about the next cycle. Solar cycle 25 suggests we may not yet know exactly what that something is. What if the machinery driving the solar cycle is not buried as deep as we thought, and we've been searching for the sun's magnetic engine in the wrong place all along? For decades, one of the most influential pictures of the solar dynamo placed much of the important action deep inside the sun, near the bottom of the convection zone. That location has a name, the tachocline. The convection zone occupies roughly the outer third of the sun by radius. In this region, hot plasma moves upward, cools as it approaches the surface and sinks again. Beneath it lies the radiative interior, where energy moves outward mainly through radiation rather than large convective flows. The two regions also rotate differently. Much of the radiative interior turns more like a solid body. The convection zone does not. At the equator, the solar surface completes a rotation faster than regions near the poles. Rotation also changes with depth. Between these different rotational regimes lies the tachocline, a relatively thin transition layer where the rotation rate changes significantly. That immediately attracted the attention of solar physicists. If you're trying to explain how a star stretches, amplifies, and reorganizes magnetic fields, a layer where enormous amounts of electrically conducting plasma move at different speeds is an obvious place to look. Magnetic fields and conducting fluids are closely connected. The sun is made largely of plasma, meaning electrons have been separated from atomic nuclei, and the material responds strongly to electric and magnetic forces. When that plasma moves, it can carry magnetic fields with it. When different parts of the plasma rotate at different rates, magnetic fields can be stretched. A field that initially runs roughly from one pole to the other can gradually be wrapped around the sun. This process helps convert what physicists call a poloidal magnetic field. with a large-scale north-south component into a toroidal field wrapped more around the direction of rotation. That toroidal field is closely connected to the magnetic structures that eventually appear at the surface as active regions and sunspots. So the tachocline looked promising. Very promising. It was deep enough that magnetic fields might be stored there without immediately rising to the surface. It contained strong rotational shear. It sat at the boundary between two regions with very different fluid behaviour. Over time, many dynamo models made the tachocline one of their most important components. NASA descriptions of solar dynamo modelling have long treated the tachocline as a leading candidate for the region, where large-scale magnetic fields are amplified and organised. Even current NASA research continues to investigate the tachocline as a potentially essential part of the dynamo, rather than considering the question settled. That last point matters because the story we are about to follow is not one where scientists believed the dynamo was deep. A new paper appeared, and everyone immediately moved it upstairs. Solar physics is not currently that tidy. The tachocline remains important in many models. But in 2024, a team led by Jeffrey Vassell published a result that made the alternative much harder to dismiss. Their argument was that important features of the solar cycle may originate not near the bottom of the convection zone, but within the outer 5 to 10% of the Sun. That is a dramatic difference. The Sun has a radius of almost 700,000 kilometers. The traditional tachocline picture places crucial dynamo processes hundreds of thousands of kilometers beneath the visible surface. The near-surface proposal moves much of the relevant machinery into a comparatively shallow region immediately below the photosphere, still deep enough that you would not want to visit. But in solar terms, almost upstairs, the region is called the near-surface shear layer, and like the tachocline, it contains an important change in rotation. Very close to the surface, the Sun's angular velocity changes with depth. At many latitudes, plasma slightly deeper in this layer rotates faster than material above it. That creates shear. Again, whenever electrically conducting plasma and rotational shear occur together, magnetic fields become interesting. The 2024 study asked whether this near-surface shear layer could produce the properties of the solar cycle that dynamo theories need to explain, not simply whether it could generate some magnetic field. That would not be enough. A useful solar dynamo model has to reproduce several things we actually observe. One of the most famous is the migration of sunspots. At the beginning of a solar cycle, new sunspots tend to appear at mid-latitudes, around 30 degrees north and south of the equator. As the cycle progresses, new active regions gradually appear at lower latitudes. Near the end, most sunspots emerge relatively close to the equator. Plot the latitude of sunspots against time, and the pattern forms shapes that resemble butterfly wings. Solar physicists call this the butterfly diagram. It is one of the clearest signatures of the 11-year cycle. A dynamo model therefore needs to explain not just why sunspots exist, but why the magnetic activity producing them migrates toward the equator in such an orderly way. Then there is another pattern called torsional oscillation. Despite the name, the entire Sun is not wobbling backward and forward. Torsional oscillations are bands where solar plasma rotates slightly faster or slightly slower than the average rotation at that latitude. These bands move across the Sun over the course of the solar cycle. Most importantly, they are closely related to the migration of magnetic activity. The bands associated with sunspot formation move toward the equator in a pattern that tracks the solar cycle. Scientists have observed these flows using helioseismology. Helioseismology works by studying waves traveling through the Sun. The visible surface is constantly moving because acoustic waves are passing through the solar interior. By measuring those oscillations carefully, researchers can infer information about rotation and flows beneath the surface. It is somewhat similar to using earthquake waves to learn about the interior of Earth. Except the object being studied is a ball of plasma large enough to fit more than 1 million Earths inside it, which makes arranging the equipment slightly inconvenient. Helioseismic observations found that the low-latitude torsional oscillations associated with the sunspot cycle are especially prominent in the outer portion of the Sun. That raised a question. If these rotation patterns and migrating magnetic activity are closely connected, why should the dynamo responsible for them necessarily begin much farther below? The 2024 Nature study argued that the near-surface shear layer provides a natural explanation. The researchers focused on a process called magnetorotational instability, usually shortened to MRI. This is not the MRI used in hospitals. No one is sliding the Sun into a medical scanner. Magnetorotational instability is a fluid instability that can occur when electrically conducting material with a magnetic field rotates at different angular velocities in different places. It is famous in astrophysics because it helps explain the behavior of plasma in accretion disks around stars and black holes. The basic idea is that even a relatively weak magnetic field can connect regions of plasma rotating at different rates. That connection can allow disturbances to grow. The instability changes the flow and amplifies magnetic effects. Vassil and his colleagues argued that conditions in the Sun's near-surface shear layer may allow this process to operate there. They compared the characteristic scales predicted by the instability with actual solar observations. According to their analysis, the near-surface mechanism could reproduce important properties of torsional oscillations and magnetic fields inferred beneath the surface. Their numerical simulations also reproduced a feature known as the hemispheric helicity rule, another observed pattern in which magnetic structures tend to have different preferred twists in the northern and southern solar hemispheres. Taken together, the authors describe the results as strong evidence that the solar dynamo may begin near the surface rather than being primarily rooted in the deep tachocline. That does not mean the tachocline suddenly becomes irrelevant. It may still influence the magnetic cycle. Deep flows may interact with shallow ones. Different parts of the dynamo may occur in different regions. The Sun is under no obligation to operate one convenient machine in one convenient layer, so we can draw a clean diagram in a textbook. In fact, NASA's Current Coffee's research program explicitly studies both the tachocline and the near-surface shear layer as regions that process and amplify magnetic fields. As recently as July 2026, NASA highlighted new modelling work in which the tachocline remained essential to dynamo behaviour, showing that the scientific debate is active rather than resolved. This is important for our discussion of Solar Cycle 25 because it would be tempting to connect the two too quickly. The official prediction underestimated Cycle 25. A near-surface dynamo theory appeared. Therefore, the deep dynamo theory must have caused the forecasting failure. That conclusion would go beyond the evidence. The 2024 paper did not demonstrate that the original Solar Cycle 25 forecast failed because forecasters placed the dynamo too deep. The consensus forecast also relied heavily on observed precursors such as the polar magnetic fields, rather than simply running one tachocline simulation and reading off a sunspot number. So the stronger than expected cycle is not direct proof that the dynamo is near the surface. What it does is make questions about the underlying magnetic model much more important. Because if the main processes controlling the solar cycle operate differently from what our models assume, prediction becomes much harder. Consider the difference between a deep and shallow dynamo from the perspective of forecasting. A deep dynamo places much of the magnetic evolution in a region we cannot directly observe. Helioseismology gives us information about flows and rotation there, but magnetic fields deep inside the Sun are much harder to measure. Researchers therefore have to infer much of what is happening. They model how the polar field is transported downward. They model how differential rotation stretches it. They model how toroidal fields strengthen. They model how those fields move toward lower latitudes. Then they model how magnetic structures become buoyant enough to rise through the convection zone and finally emerge as sunspots. Every one of those steps contains parameters and uncertainties. How fast is the circulation? How deep does it extend? How quickly does magnetic flux diffuse through turbulent plasma? How strongly are fields amplified? How long can they remain stored? How quickly do they rise? A model can reproduce the broad solar cycle while still getting some of those details wrong. That matters because two models that both produce an 11-year sunspot cycle may respond very differently when asked to predict the strength of the next one. A near-surface dynamo changes the situation. If much of the important dynamo action happens relatively close to the visible surface, then the flows involved may be more accessible to observation. Torsional oscillations can be tracked heliosysmically, surface magnetic fields can be mapped, near-surface differential rotation can be measured, active regions can be followed as they emerge and decay. In principle, a dynamo operating in a better observed part of the Sun could make prediction easier. That possibility was one of the reasons the authors of the 2024 work emphasized forecasting. If the relevant physics is near the surface and can be measured more directly, models may eventually be initialized with better observations, rather than relying heavily on uncertain conditions deep inside the convection zone. There is, however, a rather large difference between could eventually improve predictions and we can now predict the Sun. We cannot. The near-surface proposal has to survive further testing. It has to reproduce more observations. Other research groups have to test the mechanism independently. The simulations need to connect with the full solar cycle, including the development of polar fields, the formation of active regions, and the differences from one cycle to another. And perhaps most importantly, a predictive dynamo theory has to do more than explain observations after they have happened. It has to make forecasts that work before the answer is known. That is where many scientific models become uncomfortable. It is much easier to reproduce a familiar pattern when you already know what the pattern looks like. Cycle 25 has provided an especially useful test because it did not follow the expected amplitude. Any model of the solar dynamo should eventually be able to explain why. Why did the polar fields before the cycle appear to suggest something similar to cycle 24, while the resulting cycle was stronger? Was magnetic information being stored somewhere that the precursor measurement did not capture? Were near-surface flows already revealing that the next cycle would develop more rapidly? Did magnetic activity bands associated with the new cycle begin evolving earlier than expected? Was the connection between the poloidal field near minimum and the toroidal field of the following maximum modified by changes in differential rotation? Or did stochastic effects, essentially variations in when and how individual active regions emerged, amplify the cycle in ways no deterministic forecast could have captured perfectly? That last possibility deserves attention. The Sun's cycle may be regular without being completely predictable. There is a difference. A pendulum in a clock follows a regular motion that can be predicted extremely accurately. Earth's weather has seasonal patterns, but knowing the season does not tell you the exact weather on one afternoon months away. The solar cycle may sit somewhere between those examples. The broad 11-year rise and fall is regular. The magnetic polarity reversal is regular. The migration of sunspots is regular. But the exact strength of a cycle may depend on processes with enough variability that predictions will always contain substantial uncertainty. Active regions provide one source of that variability. A single large bipolar region can contribute an unusually large amount of magnetic flux. Its effect depends not only on its size but on its orientation and latitude. If it is tilted differently from the usual pattern, it can send a different amount of magnetic flux toward the poles. That changes the polar field. The polar field influences the following cycle. One unusual active region therefore has the potential to affect magnetic conditions years later. Now repeat that process for thousands of active regions. Some are ordinary, some are enormous, some have unusual orientations, some emerge at unusual times, some magnetic flux cancels locally, some crosses the equator, some reaches the poles. The solar dynamo is not operating in isolation beneath a perfectly smooth surface. It is interacting with a constantly changing magnetic environment. This makes the idea of a near-surface dynamo especially interesting, because it places the magnetic engine closer to the region where much of this variability is directly visible, but it also means the engine may be surrounded by noise, and noisy systems are difficult to forecast. There's another reason the near-surface proposal attracted attention. The migration speed of the solar cycle has always required explanation. Sunspot activity does not simply appear everywhere at once. The active bands move from higher latitudes toward the equator over roughly 11 years. Deep flux transport models often connect that migration to large-scale circulation inside the convection zone. In those models, equatorward flow at depth helps transport magnetic fields toward the equator. But the deep return flow of the Sun's meridional circulation has been difficult to measure. Near the surface, we clearly observe plasma moving generally poleward. Somewhere below, mass conservation requires a return flow. Exactly where that flow occurs, how many circulation cells exist, and how stable the pattern remains are much harder questions. Different measurements and models have produced different pictures. That creates an obvious forecasting problem. If your dynamo model depends strongly on an underground conveyor belt, you would quite like to know the speed and route of the conveyor belt. The near-surface model offers a different mechanism for the equatorward movement of magnetic activity. Instead of requiring the entire pattern to be carried by a deep flow, the migration can emerge from the behavior of the instability and the near-surface differential rotation itself. The 2024 researchers argued that this mechanism naturally reproduces the observed scale and motion of the torsional oscillations that accompany the sunspot bands. That is attractive because the torsional oscillations are observed. They are not hypothetical flows inserted because a model needs something to move magnetic fields. We can track them, and there may be forecasting information hidden inside them. Torsional oscillation bands can appear before large numbers of sunspots belonging to a new cycle become visible. That means flows beneath the surface may show signs of an approaching cycle before the obvious magnetic activity arrives. If scientists can understand the connection between those flows and the dynamo, they might gain an earlier indicator of the next cycle's development. Perhaps the sun tells us what it is preparing to do. Perhaps we have simply not learned to read all of the signals yet. That would fit the broader story of Cycle 25 remarkably well. We counted the sunspots. We measured the polar fields. We watched the cycle begin. Those indicators were useful. But something in the sun's internal magnetic evolution produced a stronger result than the original consensus expected. A dynamo theory that correctly explains those hidden processes could turn a forecasting error into a new predictive tool. A dynamo theory that merely explains the past would be less useful. And right now, both the deep and shallow pictures still have work to do. The tachocline has strong rotational shear and remains physically compelling. The near-surface shear layer has strong rotational shear too, and its connection with torsional oscillations provides evidence that important dynamo processes may occur there. Modern global simulations increasingly allow magnetic fields, convection, rotation, and circulation to interact without forcing every part of the cycle into one predetermined mechanism. Some simulations generate large-scale magnetic cycles even when the tachocline is not the sole driver. Others show that the tachocline can remain crucial. The likely answer may not be a choice between one layer and the other. The sun may operate through a dynamo distributed across much of the convection zone, with different regions controlling different parts of the cycle. That is less satisfying for a diagram. It may be more realistic for a star. That uncertainty brings us to a process that sounds simple when it's summarized in one sentence. Magnetic material from decaying active regions moves toward the sun's poles. The difficulty begins when you ask how fast it moves, which magnetic material actually reaches the poles, whether that speed stays constant, and whether the plasma flow we measure is always the same thing as the magnetic transport our models need. The answer to all four questions is more complicated than the simple diagram suggests. When a large active region appears on the sun, we normally see concentrations of opposite magnetic polarity. One part of the region has magnetic field pointing outward through the visible surface. Another part has field directed inward. These magnetic regions often appear with sunspots, although the magnetic structure extends well beyond the dark areas we can see in ordinary solar images. At first, the magnetic field can be concentrated into relatively strong regions. Then the active region ages. Sunspots shrink. The organized structure begins to break apart. Smaller magnetic elements spread into the surrounding photosphere. That does not mean the magnetic field has vanished. It has simply been redistributed. From that point, the surface of the Sun begins moving the remaining flux around. Several processes act at the same time. Differential rotation moves magnetic material east and west because different solar latitudes rotate at different rates. Small convective cells continually shuffle magnetic elements around. Larger convective structures called supergranules produce motions that make magnetic flux spread in a pattern that can be represented approximately as diffusion in many surface flux models. And beneath all of that is a large-scale north-south circulation. Near the visible surface, the average meridional flow moves plasma away from the equator and toward the poles. It is slow. Typical measured speeds are only around 10 to 20 meters per second. That is roughly the speed of a fast bicycle or a modest car in city traffic. Compared with the violent motions elsewhere on the Sun, it barely seems worth mentioning. Convective plasma at the surface can move at speeds approaching a kilometer per second. Material in a coronal mass ejection can travel hundreds or thousands of kilometers per second. The solar wind eventually passes Earth at hundreds of kilometers per second. Meanwhile, the meridional flow is moving along at something like 15 meters per second. No hurry. It has a star to cross. Despite that modest speed, the flow matters because it operates continuously over enormous distances and long periods. NASA observations have shown the surface poleward flow, extending through tens of thousands of kilometers of the Sun's outer layers, with characteristic speeds in the 10 to 20 meter per second range. If all magnetic material moved poleward equally, however, the Sun would have a problem. Both polarities from an active region would simply arrive together and largely cancel one another. The polar fields would be difficult to build. The reason they do build involves the geometry of active regions. Sunspot groups are usually tilted. The line connecting the two main magnetic polarities is not perfectly parallel to the equator. On average, the polarity that trails behind the direction of solar rotation sits slightly closer to the pole than the leading polarity. This statistical pattern is called Joy's law. The tilt is usually small, and individual active regions can behave very differently. But when thousands of regions are considered across an entire cycle, the average difference matters. The leading magnetic polarity tends to begin slightly closer to the equator. Some of that flux can move across the equator and cancel against leading polarity flux from the opposite hemisphere. The trailing polarity begins a little farther poleward. More of it survives the competition and is carried toward higher latitudes. Over time, those remnants form broad streams of magnetic flux moving toward the poles. On a magnetic butterfly diagram, scientists can actually see these streams. They appear as inclined bands stretching from the active latitudes toward the polar regions. Researchers sometimes call them poleward surges. A strong surge can take magnetic flux produced by many active regions and deliver it toward one pole. When the polarity of that arriving material is opposite to the old polar field, it begins cancelling the old field. More flux arrives. The old field weakens. Eventually, around solar maximum, the average polar field can pass through zero. Then the newly arriving polarity becomes dominant. The magnetic pole has reversed. This happens in both hemispheres, although not necessarily at the same time. Afterward, further transport strengthens the new polar fields as the cycle declines. By solar minimum, those fields become one of the measurements scientists use to predict the strength of the next cycle. So the meridional flow sits in an important position in the forecasting chain. Sunspots create the magnetic source material. Surface processes redistribute it. The meridional circulation helps move it toward the poles. The poles are rebuilt. Then researchers look at the new polar field and use it to estimate the future. If the transport is wrong in the model, the predicted polar field can be wrong. If the polar field is wrong, the predicted next cycle can be wrong. That makes the speed of the flow sound like a parameter you would want to measure very carefully. Scientists do. The uncomfortable part is that the speed does not remain constant. Observations extending across multiple cycles show that the meridional flow changes with solar activity. It tends to be faster around solar minimum and slower around maximum. There are also changes from one cycle to another. The profile changes with latitude. Flows develop around active regions. Hemispheres can behave differently. At certain latitudes and depths, the pattern becomes much more complicated than one steady conveyor belt running from the equator to the pole. Measurements covering 1996 to 2010 found that the poleward transport speed varied substantially through the solar cycle, becoming faster near minimum and slower near maximum. Researchers also observed inflows toward the sunspot belts, which reduce the average poleward flow around active latitudes. That already creates trouble for simplified models. The traditional surface flux transport model often begins with a fairly clean set of ingredients. You specify differential rotation. You specify an average meridional flow profile. You specify a diffusion coefficient representing the effects of smaller convective motions. Then you add new bipolar active regions as magnetic sources and calculate how their flux spreads across the Sun. These models have been remarkably useful. They can reproduce many large-scale features of the observed magnetic field. They can reproduce polar field reversals. They can generate recognizable magnetic butterfly patterns. They can help estimate future polar fields. The problem is that the classical version often treats processes that are changing continuously as if they were much more stable. A major 2023 review of surface flux transport described the classical model as using steady axisymmetric profiles for differential rotation and meridional flow together with uniform supergranular diffusion, while emphasizing that modern research has increasingly moved beyond those assumptions. The real Sun does not provide a steady axisymmetric flow. It provides something closer to a traffic system where the average road points north, but lanes shift, congestion develops around busy areas, some vehicles cross into neighbouring routes, and occasionally everyone decides that today is an excellent day to make the modeler unhappy. There is also a subtle distinction between measuring the plasma flow and measuring the actual motion of magnetic flux. You might expect the two to be identical. Magnetic fields in the solar photosphere are strongly coupled to the conducting plasma, so the magnetic structures are carried along by fluid motions. But what an instrument reports as an average meridional flow depends on how that flow is measured. Helioseismology can infer plasma motions beneath the surface. Magnetograms can track the movement of magnetic features. Doppler measurements can examine line-of-sight velocities. Each technique samples the system in a different way, and around active regions, local flows complicate the comparison. A study comparing poleward magnetic flux transport with helioseismic measurements found that the two generally agreed over large scales, but could differ significantly in magnetically active regions. Local circulations around active regions altered the longitudinally averaged plasma flow, while the magnetic flux did not respond in exactly the way a simple average flow profile would suggest. The researchers warned that a longitudinally averaged helioseismic flow should not automatically be inserted into a dynamo model as the magnetic transport velocity. That may sound like a technical distinction. For solar cycle prediction, it can matter enormously. Imagine that your model says magnetic flux is being carried poleward at a certain speed because that is the average plasma speed you measured, but the magnetic elements responsible for building the polar field are effectively being transported at a different rate in the regions that matter most. Your model can be based on a real observation and still move the wrong thing at the wrong speed. There is another complication. Faster poleward transport does not necessarily produce a stronger polar field. That seems counterintuitive. If the trailing magnetic polarity is supposed to reach the poles, surely moving it there faster should build a stronger field. Sometimes it can. But if the flow becomes too fast, it can also carry more of the leading polarity poleward, before that leading flux has enough time to cross the equator and cancel. Now both polarities are being delivered toward high latitudes. They cancel each other more efficiently near the pole. The final polar field can become weaker. So the relationship is not simply this: faster flow equals stronger pole. It depends on the balance between transport and cancellation. A moderate meridional flow can efficiently carry trailing polarity flux toward the pole while allowing enough leading flux to disappear across the equator. Increase the speed too much, and both polarities may be swept poleward. Recent dynamo simulations have demonstrated this non-linear behavior. Increasing meridional flow initially strengthens the polar field, but sufficiently strong flow can reduce it by carrying both polarities of bipolar regions toward the poles. This gives forecasters another unpleasant parameter. Not only do they need the flow speed, they need the correct flow speed at different latitudes. They need to know how it changes through the cycle. They need to know how active regions alter it. They need to know how deeply the circulation extends, and they need to know which measured flow most accurately represents the transport of magnetic flux. This problem existed before solar cycle 25. In fact, earlier observations had already shown that meridional flow variations could create surprising model behavior. Approaching the minimum between cycles 23 and 24, the measured surface flow became substantially faster than it had been near the previous minimum. Some flux transport dynamo models suggested that faster circulation should have produced a shorter cycle with stronger polar fields. Instead, the actual polar fields became weak, and cycle 24 was weak. Surface flux transport models could produce weaker polar fields with the faster flow, but researchers noted that some of the flow profiles used in those models did not match the observations well. The conclusion from NASA researchers at the time was unusually direct. Both kinds of model were missing identifiable components. That was more than a decade before solar cycle 25 exceeded its forecast. So the transport problem was already visible. Cycle 25 simply gave us another reason to care about it. One particularly relevant forecast was made in 2016 by David Hathaway and Lisa Upton. They used an advective flux transport model to simulate how the polar fields would evolve toward the cycle 24 to 25 minimum. Their model used observed surface flows and introduced variations in factors that could not be known perfectly, including convective motions, the tilt of active regions, and the meridional flow profile. Their results suggested that the polar fields before cycle 25 would resemble those before cycle 24, implying that cycle 25 would also be similar in strength. That was a sensible prediction. It was based on real magnetic observations. It explicitly included uncertainty. But the researchers also found something revealing. After only 4 years of simulation, the spread among their model runs had already produced about 15% uncertainty because of variations in convection, active region tilt, and meridional flow. Those errors accumulate because magnetic transport has memory. Move flux slightly differently this year, and you change where it will be next year. That changes how much cancellation happens. That changes the polar field. That changes the starting condition used to estimate the future cycle. A small transport error does not necessarily stay small. It can travel all the way into the forecast. And observations published in 2026 have made the picture even more complicated. Researchers analysed 14 years of data from the heliosysmic and magnetic imager on NASA's Solar Dynamics Observatory, covering solar cycle 24 and the rising phase of cycle 25. Instead of treating meridional circulation as one smooth surface flow, they examined how it changes with depth inside the near-surface shear layer. They found evidence that active regions modify the subsurface meridional flows, and that deeper portions of this near-surface circulation may play a major role in moving magnetic flux globally. The transport appeared episodic rather than steady. Large active regions altered the flows. Different hemispheres behaved differently. The build-up of the polar field was closely connected to plasma outflows from active latitudes in the lower part of the near-surface shear layer. One result from cycle 24 was especially striking. Stronger southern hemisphere outflows were associated with faster poleward flux transport, and the southern polar field reached its peak nearly 4 years before the northern polar field. The team found that similar broad transport patterns could also be identified in earlier cycles. In other words, a substantial part of the magnetic transport may be controlled by flows that change in response to the magnetic activity itself. That is a very different system from a model with a fixed conveyor belt. The magnetic field does not merely sit on the plasma and get carried around. The magnetic activity can modify the flows that transport the magnetic field. The transporter and the cargo affect each other. That feedback is exactly the sort of thing that makes long-range prediction difficult. Suppose a strong collection of active regions emerges in one hemisphere. Those regions add magnetic flux to the surface. They also alter local and subsurface flows. Those change flows modify how quickly magnetic material moves away from the active latitude. That changes when the flux reaches higher latitudes. The arriving flux changes the polar field. The resulting polar field becomes an ingredient in the next cycle prediction. A forecast made years earlier could not know the exact size, tilt, latitude, or magnetic complexity of every active region that would later emerge, nor could it perfectly anticipate how those regions would modify the transport system. This is why saying magnetic fields moved faster than our models captures something useful, but needs a qualification. There is not one established finding that all cycle 25 magnetic flux simply moved poleward at one universally higher speed than every prediction assumed. The reality is more interesting. Observed transport speeds vary. Magnetic flux speed can differ from the averaged plasma flow speed. Different depths can contain different flow patterns. Active regions can accelerate or redirect transport. One hemisphere can move magnetic material differently from the other, and many classical models simplify these variations into smoother profiles so the calculation remains manageable. The forecasting weakness is not necessarily that scientists entered 15 meters per second when they should have entered 17. It may be that asking for one speed is already oversimplifying the system. This becomes obvious when you look at the poles during reversal. The field does not change smoothly from positive to 0 to negative. Poleward surges arrive in separate bands. One surge may weaken the existing polar field, another may temporarily strengthen it. A later surge with opposite polarity may reverse part of that change. The north and south can follow different schedules. The average field can pause near 0. It can fluctuate. Only after enough flux accumulates does the new polarity become established. So a model predicting polar field evolution has to reproduce not just the average circulation, but the sequence of magnetic contributions moving through that circulation. And the source regions themselves are unpredictable. Joy's law gives us an average tilt. Individual active regions can ignore the average. Most behave reasonably, a few do not. A very large active region with an unusual tilt can send a disproportionate amount of magnetic flux toward a pole. One badly behaved sunspot group can therefore alter a quantity we later treat as a predictor of the next 11-year cycle. The Sun has found an efficient way of making statistical forecasting personal. You can understand the behavior of 10,000 active regions and still spend your afternoon worrying about one enormous one that has decided to point the wrong way. Cross-equatorial transport matters for the same reason. Leading polarity flux normally has a better chance of reaching the equator and cancelling with flux from the opposite hemisphere. If the source region appears closer to the equator, that cancellation becomes easier. If the region is farther away, less flux may cross. If meridional flow is stronger, leading flux may be pulled poleward before it crosses. If convective diffusion is stronger, more may reach the other hemisphere. Change any of those terms and the polar field changes. This makes surface magnetic transport one of the clearest examples of why the Sun can be understandable without being easily predictable. We know the major processes. We observe active regions emerging. We see them decay. We measure differential rotation. We measure poleward circulation. We can track magnetic elements. We can watch poleward surges appear in magnetic maps. We understand why opposite polarities cancel. We understand how the polar reversal fits into the Babcock-Leighton picture of the solar cycle. None of that is mysterious, in the sense that we have no idea what is happening. The uncertainty comes from the details, and those details determine the forecast. A difference of a few meters per second sustained over months can change how far magnetic flux travels. A shift in the flow around an active belt can change the balance between poleward transport and cross-equatorial cancellation. A change at one depth may not match the flow measured at another depth. A particularly strong active region can alter the circulation that was supposed to transport it. Over several years, all of those differences accumulate. This is why modern surface flux models increasingly use actual magnetograms and measured flows rather than relying only on idealized profiles. Data can be assimilated into the simulation as the cycle develops. New active regions can be added when they appear. Transport speeds can be updated. Observed magnetic maps can correct the modelled field. The result should become more accurate as more of the future turns into the present, but that creates the same distinction we saw with the overall Cycle 25 forecast. A model that becomes accurate after years of observations is extremely useful for operations. It is not the same as predicting the cycle before those observations exist. Long-range forecasting has to work with active regions that have not yet emerged. It has to estimate transport variations that have not yet happened. It has to predict a polar field that has not yet been built. There is a physical limit to how precise that prediction can be if random or poorly predictable active region behavior contributes significantly to the final result. Hathaway and Upton's cycle. 25 work explicitly noted that stochastic variations in convective motions, active region tilt, and changes in the meridional flow profile accumulate and limit the ultimate predictability of the cycle. That may turn out to be one of the most important lessons from the stronger than expected Cycle 25. The forecasting error may not have one cause. Perhaps the polar field measurement was imperfect. Perhaps the dynamo operates more strongly in the near-surface shear layer than many models assumed. Perhaps the magnetic transport was represented too smoothly. Perhaps active region emergence introduced variability that no forecast made at minimum could fully know. Perhaps several of those effects pushed in the same direction. Solar scientists now have something they did not have before this cycle, another complete real-world test. Every model that predicted Cycle 25 can be compared with what actually happened. Researchers can go back and ask where the simulations began to separate from observations. Did the polar field estimate start wrong? Did the modelled sunspot emergence differ? Did poleward surges arrive earlier? Did the hemispheres evolve differently? Were flow speeds incorrect? Did the model fail to capture magnetic feedback on the circulation? Those comparisons are much more valuable than simply declaring one forecast right and another wrong. They tell researchers which physics needs to change. And the transport problem connects directly to something much larger than the solar poles. Once magnetic flux reaches high latitudes, some of the sun's magnetic field extends outward into the corona. Regions of open magnetic field provide pathways along which charged particles can escape. Those particles become part of the solar wind. From Earth, the solar wind can sound almost simple. The sun continuously releases electrically charged particles into space. Those particles travel outward, past the planets, and create a large region of solar influence known as the heliosphere. For decades, spacecraft near Earth measured this flow after it had already travelled almost 150 million kilometres. By then, the solar wind usually looked relatively well developed. It had expanded. Different streams had interacted. Magnetic structures had evolved. Turbulence had changed them. Fast material had caught slower material. Disturbances had stretched, compressed, and mixed. Trying to understand how the solar wind was born from measurements near Earth was therefore a little like trying to work out how a cake was made by examining one slice several hours after it left the oven. You can learn quite a lot. You can identify the ingredients. You can measure the texture. You can probably tell whether someone used far too much chocolate. But there are parts of the preparation you simply did not see. Parker Solar Probe was built to get much closer to the kitchen. NASA launched the spacecraft in August 2018 and named it after Eugene Parker, the physicist who had predicted the existence of the solar wind in 1958. Instead of remaining near Earth and waiting for solar particles to arrive, Parker Solar Probe repeatedly swings close to the Sun, using Venus flybys to reduce its orbit and move deeper into the solar environment. Its instruments measure particles, magnetic and electric fields, energetic particles, and structures in the solar wind while that wind is still relatively young. That approach immediately changed the picture. Near Earth, the solar wind often appears like a fairly continuous flow. Closer to the Sun, Parker found something much less orderly. The wind came in bursts. Its magnetic field repeatedly changed direction. Streams varied in density and speed. Particles arrived in structures that had not yet been smoothed out by millions of kilometers of travel. One of the biggest surprises appeared during Parker's early encounters. The spacecraft repeatedly detected sudden reversals in the direction of the magnetic field. These structures are called switchbacks. Imagine following a magnetic field line that generally points away from the Sun. For a short distance, the field suddenly bends backward. Then it turns again and resumes its original direction. A spacecraft passing through that structure sees the magnetic field rotate sharply. Earlier missions had occasionally detected similar features, so switchbacks were not completely unknown. What Parker discovered was how common they are near the Sun. They appeared in clusters. Sometimes the magnetic field was filled with them. Instead of a neat set of lines extending smoothly outward, Parker encountered a solar wind containing repeated bends, reversals, and bursts of plasma. NASA's later summaries of the mission described switchbacks as much more common near the Sun than researchers had expected. That immediately created several questions. Where do these switchbacks come from? Do they form in the corona? Are they created farther out as the solar wind becomes turbulent? Do they provide energy to the wind? Or are they simply magnetic traces left behind by some more fundamental process near the solar surface? Parker gradually moved close enough to narrow down the possibilities. The switchbacks appeared to connect back towards small magnetic structures near the photosphere, especially regions associated with magnetic funnels. Those funnels tend to occur around the boundaries of supergranules. Supergranules are large convection cells visible in the pattern of motions near the Sun's surface. Hot plasma rises, spreads outward, and then sinks around the edges of these cells. As plasma moves toward those boundaries, magnetic field becomes concentrated there. The result is a network of stronger magnetic structures. Some magnetic field lines form closed loops. They leave the surface and return to it nearby. Others extend outward into the corona and eventually into interplanetary space. Those are described as open magnetic fields. The distinction becomes important because particles can escape more easily along open field lines. Now suppose a closed magnetic loop sits beside an open field line. The two magnetic structures interact. Under the right conditions, their connectivity can change through magnetic reconnection. A portion of previously closed field can become connected to open space. Plasma that had been confined on the closed loop suddenly gains access to a route outward. Energy stored in the magnetic field can also be released during the process. The result can be a burst of plasma moving away from the Sun. This specific type of interaction is known as interchange reconnection. For years, it had been suggested as one possible source of the solar wind. Parker gave scientists a chance to test the idea much closer to where the process might actually happen. In 2023, researchers reported Parker measurements of fast solar wind streams coming from a coronal hole. The streams carried structure corresponding to the supergranulation pattern on the surface. They arrived in bursty patches containing switchbacks and energetic ions. Simulations of interchange reconnection reproduced several important features of the observations, and the researchers concluded that the process could provide enough energy to help power fast solar wind from coronal holes. That matters because coronal holes are important sources of fast solar wind. A coronal hole is an area of the corona where the magnetic structure is relatively open. In extreme ultraviolet images, these regions often appear darker because the plasma there is less dense and cooler than nearby coronal structures. Open magnetic fields provide channels along which plasma can escape outward. Near solar minimum, large coronal holes often form near the poles. That connects directly with the polar magnetic fields we've just been discussing. The poles help organize open magnetic flux. Open magnetic flux shapes the solar wind. The solar wind carries the sun's magnetic field outward, and eventually that magnetic environment reaches Earth. So the polar field measurement used to forecast the next solar cycle is connected to the same global magnetic structure that helps determine what kind of solar wind spreads through the solar system. But Parker showed that even the fast wind coming from relatively clean open field regions is not simply a steady stream escaping through a large hole. At smaller scales, it can be produced through repeated magnetic interactions. Tiny reconnection events may be releasing plasma in separate bursts. Those bursts may create switchbacks. The switchbacks may contain part of the energy that accelerates the wind. In other words, what looks like a continuous solar breeze from Earth may begin as countless separate magnetic events. Imagine standing far downstream from a waterfall. The river looks smooth. Move close to the falling water and suddenly there are individual droplets, jets, vortices, and splashes. The average flow was not wrong, it simply hid the smaller structure. Parker Solar Probe did something similar for the solar wind, and the closer it went, the less smooth the boundary between the sun and the wind became. There is a region where solar plasma changes from material that is still magnetically connected strongly enough to communicate back toward the sun into material that is escaping outward too quickly for those disturbances to return. The important boundary is called the Alfvén critical surface. Inside it, disturbances known as Alfvén waves can move through the plasma fast enough that information can still travel back toward the sun. Outside it, the outward solar wind is moving faster than those waves can propagate back against the flow. Beyond that point, the plasma has effectively escaped. It is becoming the solar wind that continues through the heliosphere. Before Parker, scientists knew this boundary should exist. They did not know exactly where it was or what shape it had. A simple diagram might tempt you to draw a smooth shell around the sun. Parker did not find a smooth shell. In April 2021, during one of its close approaches, the spacecraft crossed the Alfvén critical surface and entered the corona. Then it left. Then it entered again. The crossing showed that the boundary was uneven. It moved outward in some places and inward in others. The sun's atmosphere did not end at one fixed distance. That became even more interesting as solar cycle 25 intensified. By combining repeated Parker measurements with observations from other spacecraft, researchers later began mapping how the Alfvén surface changed during the solar cycle. Results published in 2025 indicated that as solar activity increased, the boundary became larger, rougher, and more irregular. Instead of maintaining one stable shape, the regions separating the magnetically connected corona from the escaping solar wind changed with the sun's activity. That gives solar cycle 25 another useful role. The unexpectedly strong cycle did not merely provide more sunspots for scientists to count. It allowed Parker to sample the near-sun environment while the sun was becoming highly active. The spacecraft could compare conditions from quieter periods with the much more complicated corona around maximum, and this is exactly the kind of observation that solar models need. A model may work well when the sun is quiet. Open magnetic regions are relatively organized. Large coronal holes can dominate some areas. The global magnetic field looks more like a simple dipole. Then solar maximum arrives. Active regions appear across the surface. Magnetic loops become abundant. The polar fields reverse. The large-scale magnetic field becomes much more complicated. Coronal holes appear at different latitudes. Flares and coronal mass ejections become more common. The solar wind has to emerge through all of that changing structure. If a model represents the solar wind using one fixed boundary or one simple source region, maximum provides a rather aggressive test. Solar Cycle 25 provided plenty of testing. Parker's record-setting December 2024 encounter took it only about 3.8 million miles, or roughly 6.1 million kilometers, above the solar surface. During closest approach, it was moving at approximately 430,000 miles per hour. That made it both the closest spacecraft ever to the Sun and the fastest human-made object. At that distance, the probe was not examining a distant solar wind that had spent days rearranging itself. It was observing plasma and magnetic structures shortly after they left the corona. The spacecraft's Whisper camera also produced the closest ever images of the solar wind. Those images showed structures that become much harder to distinguish farther away. Among them were multiple coronal mass ejections interacting with one another. That is especially important for space weather forecasting. When one CME moves through interplanetary space, researchers can estimate its speed and direction and try to predict when it may reach Earth. Now put another CME behind it. The second eruption may be faster, it can catch the first. Their plasma can compress. Their magnetic fields can interact. Their trajectories can change. Particles can be accelerated. A third eruption can complicate the situation further. During the December 2024 encounter, Parker's close-up observations showed multiple CMMEs piling into one another in much greater detail than researchers had previously seen so close to the Sun. NASA researchers noted that these interactions can alter trajectories and mix magnetic fields, both of which matter for predicting effects farther from the Sun. This brings us back to the central forecasting problem. Knowing that a CME is heading toward Earth is useful. Knowing its magnetic orientation when it reaches Earth is often even more important. Earth has its own magnetic field. When the magnetic field carried by incoming solar plasma has a strong southward component, it can interact especially efficiently with Earth's northward field on the day side through magnetic reconnection. That allows energy from the solar wind to enter Earth's magnetosphere more effectively. A CME with an unfavourable magnetic orientation may therefore produce a much stronger geomagnetic storm than another CME travelling at a similar speed. The difficulty is that the magnetic field inside a CME can evolve while travelling toward us. If CMEs collide, the problem becomes even harder. So understanding them close to the Sun gives forecasters better information about their starting conditions. Parker cannot solve that problem by itself. Its orbit takes it through one part of a huge three-dimensional environment. The Sun may erupt somewhere else. A CME can pass far from the spacecraft. No single probe can sit everywhere at once. Even very expensive spacecraft remain disappointingly unwilling to duplicate themselves when scientists need more measurements. But Parker provides direct samples from a region we previously understood mainly through remote observations and models. That has already exposed several places where the simple picture was incomplete. The solar wind is more structured near its source. Switchbacks are common. The Alphen boundary is irregular. The shape of that boundary changes with solar activity. Fast wind can be linked to small-scale magnetic structure and interchange reconnection. The slow solar wind, meanwhile, remains more complicated. Slow solar wind is not simply the fast wind moving badly. It has different properties. NASA describes it as denser and more variable than fast wind, with typical speeds around 180 to 300 miles per second. Parker observations have supported evidence for at least two broad types of slow solar wind. One is alphenic, meaning it contains magnetic fluctuations and switchbacks similar in some respects to the fast wind. The other is non-alphenic and lacks the same type of magnetic variability. Researchers suspect these two forms may come from different solar environments. Alphenic slow wind may originate near coronal holes and their boundaries. Non-alphenic wind may be associated more strongly with helmet streamers, large coronal structures formed above closed magnetic regions. As of NASA's 2025 assessment, scientists still did not have a final consensus on the origins of the slow wind. That uncertainty is important because slow and fast wind eventually interact. The sun rotates while releasing both. A faster stream can catch a slower stream ahead of it. Material becomes compressed where they meet. Magnetic fields become compressed as well. These regions can create geomagnetic disturbances even without a major CME. So forecasting space weather requires more than predicting dramatic eruptions. It requires understanding the ordinary background wind into which those eruptions travel. And the background is not particularly ordinary once you examine it closely. Magnetic reconnection appears throughout this story because it is one of the main ways magnetic energy is rapidly converted into particle motion and heat. We have already seen it as a possible source of bursts feeding the solar wind. It also plays a major role in flares and eruptions. Where magnetic structures become stressed, oppositely directed fields can rearrange their connectivity. Energy stored in the magnetic configuration is released. Particles accelerate. Plasma heats. Material can be thrown outward. The basic process is well established. The details are still capable of producing surprises. In April 2026, NASA reported a new analysis of an event Parker had encountered during a 2022 flyby. The spacecraft passed between the Sun and a magnetic reconnection region in the solar wind, and measured particles accelerated by the event. Researchers expected protons and heavier ions to show similar acceleration patterns. They did not. The protons formed a more dispersed beam, while heavier ions were directed much more narrowly. That difference was not what standard reconnection expectations predicted, and researchers are using the measurements to refine models of how magnetic explosions accelerate particles. That result is useful for a very simple reason. Solar storms are magnetic explosions. The particles accelerated during strong events can become hazards for spacecraft and astronauts. If our reconnection theories still miss details about how different particles are accelerated during a directly measured event, then predictions of energetic particle environments will also contain uncertainty. Again, this does not mean scientists know nothing. It means the closer we get to the physical process itself, the more detail appears. From far away, magnetic reconnection can be represented as two field structures coming together, reconnecting, and releasing energy. Measure the particles directly and you discover that different species may respond differently. Measure the magnetic field directly and you find switchbacks. Cross the edge of the corona directly and you find that the boundary is not smooth. Watch CMEs close to the Sun and you find them colliding and changing one another before they have travelled very far. Parker Solar Probe has repeatedly turned clean diagrams into more complicated measurements. That is exactly what the mission was supposed to do. The important question for Solar Cycle 25 is what those measurements tell us about prediction. The unexpectedly strong cycle showed that we had underestimated the amount of solar activity. Parker is showing that even once activity occurs, the mechanisms that turn solar magnetism into outward-moving plasma are more structured and variable than models once represented. Predicting the number of sunspots is one problem. Predicting how magnetic energy leaves those sunspots and surrounding regions is another. Predicting how that energy becomes solar wind, flares, energetic particles, and CMEs adds more layers. Then the material has to travel through interplanetary space. Different streams interact. CMEs merge. Magnetic fields rotate. Particles accelerate. Finally, whatever survives that journey arrives at Earth, where another magnetic interaction determines how serious the effects will be. A solar forecast therefore has to connect processes occurring at very different scales. Flows below the photosphere, magnetic fields at the surface, open and closed structures in the corona, reconnection, particle acceleration, the solar wind, the heliosphere, Earth's magnetosphere. An error near the beginning can affect everything that follows. Parker improves one part of that chain by moving measurements closer to the source. Instead of waiting until the solar wind reaches Earth, scientists can study it before much of its structure has been erased or altered. They can compare switchbacks with magnetic features on the surface. They can measure turbulence while it is developing. They can sample particles close to reconnection regions. They can watch the boundary of the corona change during the solar cycle. That provides better physics for the models. Parker Solar Probe can fly through the Sun's outer atmosphere and sample the plasma leaving it, but there is one basic problem it cannot solve simply by getting closer. The view. Almost every detailed image humans have taken of the Sun has come from roughly the same direction. Earth travels around the Sun in a nearly flat orbital plane called the ecliptic. Most of the planets follow approximately the same plane. And because launching spacecraft onto radically tilted solar orbits requires a great deal of energy, most solar observatories have remained close to that plane as well. That gives us an excellent view of the solar equator and mid-latitudes. It gives us a much less useful view of the poles. We can see toward them, of course, but we normally see them at a shallow angle, close to the upper and lower edges of the solar disk. That makes measurements difficult. Features become compressed by perspective. Some of the highest latitude surface is hidden by the curvature of the Sun. Measurements of magnetic fields become less certain because instruments are often trying to determine the direction and strength of a field while looking at it almost sideways. And this is particularly inconvenient because, as we have already seen, the poles are not minor parts of the solar cycle. They are deeply involved in the magnetic reversal. They are built from magnetic material transported out of the active regions. Their strength near solar minimum is one of our most important predictors of the next cycle. Large amounts of open magnetic flux extend outward from high latitudes and help shape the solar wind. So for decades, scientists were trying to understand some of the most important magnetic regions on the Sun from one of the least convenient viewing angles available. Solar Orbiter was designed to change that. The spacecraft launched in February 2020 as a European Space Agency mission with major NASA participation. Its job is not merely to photograph the Sun from closer range. It carries 10 scientific instruments designed to connect what happens on the visible Sun with the plasma, particles, magnetic fields, and solar wind moving through the space around the spacecraft. Some instruments look remotely at the Sun. Others directly measure the environment Solar Orbiter flies through. That combination is extremely useful. A telescope might identify a magnetic structure on the surface. Another instrument can observe the corona above it. Then the spacecraft may later measure plasma associated with that region after it has escaped into space. Instead of studying the source and the resulting solar wind as completely separate problems, researchers can try to connect them. But Solar Orbiter's most unusual feature is its orbit. The spacecraft has been using repeated encounters with Venus to gradually tilt its path away from the ecliptic. During a gravity assist, a spacecraft passes close enough to a planet for the planet's motion and gravity to change the spacecraft's trajectory. Mission planners can use that effect to alter speed and direction without carrying the enormous amount of fuel that would otherwise be required. Solar Orbiter is using Venus almost like a series of carefully positioned ramps, except the ramps are planets moving tens of kilometers per second. So it is probably better not to think about the driving instructions too literally. In February 2025, a Venus flyby increased Solar Orbiter's inclination from around 7.7 degrees to approximately 17 degrees relative to the solar equator. ESA plans another Venus encounter on December 24, 2026 that should raise the inclination to about 24 degrees, with later flybys eventually pushing it to around 33 degrees during the extended mission. 17 degrees does not sound enormous. If you tilted your head by 17 degrees while reading this, nobody in the room would call the emergency services. But for solar observing, it changed something fundamental. In March 2025, Solar Orbiter began looking directly enough toward the solar poles to obtain views no imaging spacecraft had previously achieved. On March 23rd, it observed the Sun from about 17 degrees below the solar equator. A few days earlier, during its first high-angle observing campaign on March 16th and 17th, it had already been looking from roughly 15 degrees below the equator. For the first time, scientists could clearly examine the South Polar region from outside the usual ecliptic perspective. There had been one important mission before Solar Orbiter that travelled over the Sun's high latitudes, Ulysses. Launched in 1990 as an ESA and NASA mission, Ulysses used Jupiter's gravity to move into an orbit that carried it above and below the solar poles. It produced valuable measurements of the solar wind, particles and magnetic field at high latitudes. But Ulysses did not carry imaging telescopes. It could measure the environment where it travelled, but it could not look back at the polar surface with the kind of magnetic and ultraviolet imaging instruments available today. Solar Orbiter combines the high-latitude perspective with telescopes. That distinction is what makes the current observations new, and the timing turned out to be unusually useful. Solar Orbiter reached this new viewing angle while the Sun was around solar maximum. That meant the poles were going through one of the most complicated stages of their magnetic cycle. If the spacecraft had arrived near solar minimum, scientists might have seen something much cleaner. Around minimum, the Sun's large-scale magnetic field often resembles a relatively organised dipole. One magnetic polarity dominates near one pole, the opposite polarity dominates near the other. During maximum, that arrangement breaks down. Magnetic material carried out of the active latitudes reaches the poles. The old polar fields weaken, they reverse, and while that reversal is happening, magnetic regions of both polarities can occupy the same polar area. That is exactly what Solar Orbiter saw. Its polarimetric and helioseismic imager, known as PHI, mapped the magnetic field around the South Pole. Instead of revealing one clean magnetic polarity, the measurements showed patches of both signs extending right into the polar region. The North Pole also showed a mixed pattern during the pole-to-pole observations. ESA described the polar magnetism during this stage as highly mixed, which is expected while the global magnetic field is reversing around solar maximum. Over time, one polarity should gradually become dominant again as the Sun moves toward its next minimum. The important part is not that scientists were shocked to discover mixed polarity. They expected the field reversal to be complicated. What they had not previously been able to do was observe the process this clearly from above the usual viewing plane. That gives researchers a chance to test the assumptions built into magnetic maps produced from Earth. Remember the problem with those maps. Near Earth's viewing plane, the higher solar latitudes sit close to the edge of the disk. Magnetic measurements become more uncertain. Some data have to be corrected for projection. Regions that cannot be measured well may have to be estimated using observations taken at different times. A model then turns those measurements into a representation of the polar field. That representation can be extremely useful. It is still not the same thing as measuring the region from a better angle. Solar Orbiter can now compare the two. Scientists can ask whether the field strength inferred from the traditional viewpoint matches what PHI measures from higher latitude. They can look at whether small magnetic structures were missed. They can examine how the average polar field emerges from many individual magnetic patches, and they can follow those patches as the polar reversal progresses. This is especially relevant after solar cycle 25. The polar fields before the cycle were one of the major reasons scientists expected activity similar to the weak solar cycle 24. Cycle 25 came in substantially stronger. That does not prove the old polar measurements were wrong, but now scientists have a better way to investigate whether viewing geometry contributed to the forecasting error, and the first polar observations already show why reducing the poles to one average number can hide a great deal of structure. PHI's full magnetic maps showed the strongest magnetic concentrations in broad active bands close to the equator, where sunspots were abundant. Up at the poles, the field looked weaker on average, but was divided into many smaller red and blue magnetic patches. Those patches matter because the global polar field is the combined result of all of them. When researchers say that a polar field has a particular strength, they are averaging over a region that contains far more detailed magnetic structure. During reversal, positive and negative contributions can exist side by side. A small change in which magnetic patches reach the pole, how long they survive, or how quickly they cancel can affect the average field that eventually develops. Solar Orbiter can now watch that process with a viewing angle that improves as the mission continues, and magnetism is only one part of what the spacecraft is measuring. The Extreme Ultraviolet Imager, or EUI, observes the hot solar atmosphere above the surface. In ultraviolet light, the photosphere is no longer the main thing we see. The corona becomes visible. Magnetic loops filled with hot plasma rise above active regions. Bright structures appear where energy is being released. Darker areas can indicate regions where the corona is less dense and magnetic field is more open. When EUI looked toward the South Pole in March 2025, the polar region appeared relatively darker and calmer than the more active bands at lower latitudes, while million-degree plasma could still be seen forming structures and occasional jets in the corona. Those jets are interesting because the polar regions are closely connected to open magnetic field. Near solar minimum, large polar coronal holes can become major sources of fast solar wind. Around maximum, the magnetic geometry is more complicated. Open field regions shift. The poles reverse. Active regions appear across a wider range of latitudes. Solar Orbiter gives scientists a way to watch how the polar corona changes while that magnetic reorganization happens underneath it. Another instrument, SPICE, adds a different kind of information. SPICE stands for Spectral Imaging of the Coronal Environment. Instead of simply taking an image showing brightness, it separates sunlight into spectral lines produced by different elements and ions. Different lines form most strongly at different temperatures. That allows scientists to investigate layers of the solar atmosphere containing plasma at different conditions. During the 2025 polar observations, SPICE did something especially useful. It measured the motion of solar material using the Doppler effect. The same basic effect changes the pitch of an ambulance siren as it approaches and then moves away. With light, motion toward or away from an observer shifts the wavelength of spectral lines. Measure the shift carefully enough, and you can estimate how quickly the emitting plasma is moving along the line of sight. SPICE produced velocity maps showing carbon ions moving through the transition region, the thin part of the solar atmosphere where temperatures rise dramatically between the lower atmosphere and the corona. Some patches showed faster motions associated with small jets and plumes. From high latitude, these Doppler measurements are particularly valuable because earlier observations of polar outflows suffered from the same grazing angle problem as magnetic measurements. Solar Orbiter can begin looking more directly along the direction in which some polar material is moving. ESA has emphasized that this improved geometry should help researchers determine how plasma begins its journey outward into the solar wind. That connects Solar Orbiter directly with Parker Solar Probe. Parker samples the wind close to the Sun after plasma has already escaped into the corona and begun accelerating outward. Solar Orbiter can look at the source regions where that material starts moving. One spacecraft can measure the departing traffic. The other can examine the junction where some of it entered the motorway. And because Solar Orbiter also carries instruments that directly sample particles and magnetic fields around the spacecraft, it can sometimes do both jobs itself. This combination may help solve one of the questions Parker raised. Where exactly does different solar wind come from? Fast solar wind is strongly associated with open magnetic regions such as coronal holes. But Parker found that the fast wind near the Sun is structured into bursts and magnetic switchbacks. Interchange reconnection may release plasma where open and closed magnetic fields meet. Solar Orbiter's high-latitude observations can map those open regions from an angle that makes their polar structure much easier to study. Then scientists can compare those observations with what spacecraft later measure in the wind. If a jet leaves a polar magnetic structure, does it correspond to a burst measured farther out? Do certain magnetic configurations produce more switchbacks? Does the composition measured by SPICE match the material later detected in situ? How does the fast wind change as the polar field becomes more organised toward minimum? These are questions that require repeated observations rather than one photograph. That is why solar orbiters' increasing inclination matters more than the first image itself. The first polar view was historically interesting. The scientific value comes from watching the region change. The spacecraft is expected to continue observing both poles as the Sun moves away from the maximum of cycle 25. The mixed magnetic polarities should gradually reorganize. One polarity should strengthen at each pole. Poleward magnetic surges should continue delivering flux from lower latitudes. Coronal structures should change as the large-scale field becomes simpler. The distribution of open flux should evolve. By the time the Sun approaches the next minimum, scientists may have followed much of the process that creates the very polar field they will use to predict solar cycle 26. That is something researchers did not have when they forecast cycle 25. The field used in the cycle 25 prediction was observed mainly from near the ecliptic. The field used in the next prediction may be observed partly from above it. That provides an obvious experiment. Do better polar measurements improve the forecast? If they do, then part of the cycle 25 problem may have been observational. If they do not, then scientists will have to look harder at the dynamo, surface transport, active region variability, or the relationship between polar magnetism and future sunspot activity. Either result would be useful. This is one of those situations where discovering that the instrument was not the problem would still count as progress. It would simply mean the model has fewer places to hide. Solar Orbiter may also reveal patterns at the poles that are not currently represented well in models. ESA researchers have specifically mentioned the possibility of looking for large-scale polar vortices or other organised motions in the solar atmosphere. Similar polar circulation patterns appear on planets such as Venus and Saturn. The Sun is obviously not an atmosphere sitting on a solid planet, so the physics is different, but high-latitude flows may still contain structures that were difficult to recognise from the ecliptic. Even without some unexpected giant vortex, ordinary polar flows could matter for the magnetic cycle. The surface meridional circulation delivers magnetic flux toward the poles. Deeper and smaller scale flows may redistribute it. Differential rotation extends to high latitude. The poles are therefore not passive bins where magnetic material is deposited at the end of the cycle. They are dynamic regions where field, plasma and circulation continue interacting. And because our old view compressed those motions close to the edge of the solar disk, we may have simplified them more than we realised. Solar Orbiter's orbit will make the comparison increasingly useful. At 17 degrees, the view in 2025 was already unprecedented. After the planned Venus flyby in December 2026, the orbit is expected to reach about 24 degrees. Later, from June 2029 onward, ESA plans for the inclination to rise to around 33 degrees. At that angle, Solar Orbiter will not be directly above the pole, but it will have a far better view than anything available from Earth or from other current solar observatories. The mission also approaches the Sun to around 0.29 astronomical units during many perihelia, putting it well inside Mercury's orbit and giving its telescopes a detailed view while its instruments sample the surrounding plasma. That balance between proximity and latitude is what makes the mission unusual. Parker gets much closer. Solar Orbiter gets a broader observational toolkit and a better polar angle. Together they approach the same problem from different directions, and the problem is not merely why the Sun has spots, it is how a changing magnetic field inside the Sun becomes the activity that affects the rest of the solar system. The poles sit in the middle of that process. They preserve the magnetic result of one cycle. They help provide the initial conditions for the next. They connect with open magnetic fields extending into the corona. They contribute to the structure of the solar wind. They change polarity while the sun is most active. And until 2025, we had never imaged them clearly from outside the usual orbital plane. That is a remarkable limitation when you consider how confident some solar diagrams can look. There is the sun, here is the North Pole, here is the South Pole, here are the field lines, very neat. The real map from PHI during maximum looks less like a school diagram and more like someone emptied 2 boxes of magnetic confetti onto the surface. Both polarities are present, structures change, flux is still arriving, the final field has not settled, and that unsettled state may be exactly what scientists need to observe. Because the transition from mixed magnetism to a strong, organised polar field is part of the process our forecasting models have to reproduce. A model that simply begins with the finished polar field is missing the history that created it. Solar Orbiter can follow more of that history. It can measure which magnetic patches move poleward. It can see how they cancel. It can track the growth of the dominant polarity. It can compare surface field with coronal structure. SPICE can measure motions in the atmosphere above the poles. EUI can watch jets and hot plasma. PHI can map magnetism and study motions through helioseismology. The spacecraft's in-situ instruments can measure particles, fields, and solar wind farther out. That creates a connected set of observations rather than one isolated number at minimum. And perhaps that is what solar prediction has been missing. The sun does not produce a new cycle from one number. The polar field strength is useful because it summarizes part of the magnetic state. But the real system includes the history of magnetic flux emerging, dispersing, moving toward the poles, reversing the old field, creating open structures, interacting with the corona, and eventually feeding the heliosphere. The more of that process scientists can observe directly, the less they have to assume. Solar Cycle 25 showed that some of those assumptions were not good enough. Solar Orbiter arrived at the poles at almost an ideal moment to find out which ones. Yet even a perfect map of the polar field would not solve the most immediate danger from solar activity. Knowing how a cycle develops tells us something about how often strong events may occur. It does not tell us exactly when a magnetic region will suddenly release its stored energy. The May 2024 storms demonstrated that distinction very clearly. The sun can spend days building a complicated active region. Magnetic fields twist and shear. Energy accumulates. Then, within minutes, magnetic reconnection can reorganize the system and produce a powerful flare. A coronal mass ejection may follow. The problem becomes much more immediate once that magnetic energy stops being part of the sun's internal cycle and starts moving toward Earth. Because a stronger solar cycle does not damage a satellite simply by having more sunspots. A sunspot can sit on the visible surface for days and do very little to us. The danger begins when magnetic energy stored around an active region is released, and one of the main processes responsible for releasing it is magnetic reconnection. We have already encountered reconnection while looking at Parker Solar Probe and the solar wind, but during a major solar eruption the scale can become enormous. An active region can contain loops of magnetic field extending high into the solar atmosphere. The plasma around those fields moves. The sun rotates. New magnetic flux emerges from below. Different parts of the photosphere shear past one another. Loops become twisted and stressed. Energy accumulates in the magnetic field. For a while, the system can remain stable. That does not mean nothing is happening. It means the magnetic structure is storing energy without releasing most of it. Then the configuration changes enough for magnetic reconnection to occur. The connectivity of the magnetic field rapidly rearranges. Magnetic energy is converted into heat, radiation, plasma motion, and energetic particles. NASA describes reconnection as a key process behind solar flares, coronal mass ejections, and energetic particle events. It also occurs much closer to home, where the magnetic field carried by the solar wind reconnects with Earth's magnetosphere. This is why one magnetic process appears at several different points in the story. Reconnection can help release a solar eruption. Then, after that eruption crosses interplanetary space, reconnection can help transfer its energy into Earth's magnetic environment. The same basic physics is involved, but the setting changes. On the Sun, a major reconnection event may produce a bright solar flare. A flare is electromagnetic radiation. X-rays, ultraviolet radiation, visible light, radio emission, and other wavelengths can all increase during a strong event. Because that radiation travels at the speed of light, Earth receives it only about 8 minutes after it leaves the Sun. There is no spacecraft halfway between here and the Sun that can warn us 10 minutes before the light arrives. The flare reaches every observer near Earth at essentially the same time we detect it. That means some space weather effects begin almost immediately. Strong X-ray and extreme ultraviolet radiation can change the ionization of Earth's upper atmosphere on the sunlit side of the planet. High-frequency radio signals may then be absorbed rather than reflected as expected. This can produce radio blackouts. A large flare may therefore affect communications before most people have even heard that an eruption occurred. The Sun does not send a calendar invitation. A different threat can arrive minutes to hours later. During some eruptions, protons and other charged particles are accelerated to extremely high energies. These solar energetic particles can travel through the solar system much faster than the bulk material in a coronal mass ejection. They're especially important for spacecraft electronics and astronauts. People on Earth are protected by the atmosphere and magnetosphere. Someone travelling beyond much of that protection does not have the same luxury. Radiation exposure becomes a serious operational concern. Then comes the slower part of the event, the coronal mass ejection. A CME is a huge eruption of plasma and magnetic field from the Sun's corona. Some move relatively slowly, others leave the Sun at well over 1 million miles per hour. The fastest can reach Earth in roughly a day. Slower ones may take several days, and unlike a flare, which is radiation, a CME is an actual moving structure. It contains solar plasma, it carries magnetic field, it expands as it travels, it can rotate, it can be deflected, it can interact with the ordinary solar wind, and, as Parker Solar Probe has shown, separate CMEs can catch one another and combine into a much more complicated disturbance. This is where predicting a solar storm becomes much harder than simply detecting an explosion. Once an eruption appears in coronagraph images, forecasters can estimate its direction. They can measure how quickly it seems to be expanding. They can estimate whether Earth lies in its path. Computer models then propagate the disturbance outward through the solar wind and estimate when it may reach us. That part of forecasting has improved considerably. The difficult part is predicting exactly what magnetic field will be inside the structure when it arrives. NOAA notes that a CME's speed, size, direction and density can be estimated from remote observations, but its magnetic field strength and direction cannot currently be determined with the same certainty until the disturbance reaches a monitoring spacecraft ahead of Earth. That magnetic orientation is critical for judging how strong the resulting geomagnetic storm may become. This brings us to one of the most important directions in space weather, south. Earth's magnetic field near the dayside points generally northward. The magnetic field carried through interplanetary space can point in many directions. Researchers often describe its north-south component using the term BZ. When the incoming magnetic field is strongly southward, it points opposite to Earth's field at the dayside boundary of the magnetosphere. That configuration favours magnetic reconnection. The solar magnetic field and Earth's magnetic field can change connectivity. Energy and plasma are transferred into the magnetosphere much more efficiently. If the incoming field remains strongly southward for a long period, the geomagnetic response can become severe. Two CMEs can therefore arrive with similar speeds and produce very different results. One may contain a field that is poorly oriented for sustained coupling with Earth. Another may arrive with a strong southward field and maintain it for hours. The second event can produce the more serious storm even if a photograph of the original eruptions made the first one look equally impressive. This is one reason flare strength alone does not tell you how dangerous an event will be at Earth. An X-class flare may occur without an Earth-directed CME. A moderate flare may accompany a CME whose magnetic field later becomes highly effective at driving a geomagnetic storm. NASA highlighted exactly this forecasting problem after an April 2023 event. The CME did not initially look exceptional, yet the resulting geomagnetic storm became severe. Later analysis suggested fast solar wind from a nearby coronal hole deflected and rotated the CME so that its magnetic field arrived in a configuration that coupled much more effectively with Earth. That is a remarkably useful example. The eruption did not have to become much larger, its orientation changed, and that changed what Earth experienced. Now imagine trying to predict that orientation 2 days in advance from a distant image of the CME leaving the Sun. You can see why this remains difficult. By the time the disturbance approaches Earth, forecasters have better information. Several spacecraft operate near the L1 Lagrange point, roughly 1 million miles toward the Sun from Earth. A solar wind structure headed directly toward us normally passes those spacecraft before reaching Earth. Instruments measure the plasma speed, density, and magnetic field. At that moment, forecasters can finally see important properties of the incoming magnetic field directly. If BZ turns strongly southward, the expected storm can be upgraded. The disadvantage is distance. L1 is only a small fraction of the way from the Sun to Earth. Depending on the speed of the solar wind or CME, the warning provided by direct upstream measurements may be on the order of tens of minutes. NASA notes that the usual lead time from L1 measurements is around 10 to 60 minutes. That is useful. Grid operators can make changes. Satellite operators can prepare spacecraft. Warnings can be updated, but it is not much time if the event is extreme. Your star has travelled roughly 150 million kilometres to deliver a magnetic problem, and you may learn one of the most important details during the last million miles. This limitation became very visible in May 2024. The active region responsible for the event, AR 3664, became enormous and magnetically complicated. From May 3rd through May 9th, NASA's Solar Dynamics Observatory recorded 82 notable solar flares. Several coronal mass ejections were launched toward Earth. Some travelled at speeds reaching about 3 million miles per hour. Instead of arriving as isolated events, they bunched together. The first disturbances reached Earth on May 10th. Conditions were suitable for strong coupling. The resulting geomagnetic storm reached G5 on NOAA's scale, the highest category and the first G5 event since 2003. The public saw auroras. Scientists saw a full system experiment. When solar plasma began interacting with Earth's magnetic field, the magnetosphere was compressed on the day side. Reconnection transferred energy into the system. That energy was then stored and redistributed. Some of it moved into the long magnetic tail stretching away from the Sun on Earth's night side. Reconnection can occur there too. Field lines in the magnetotail can rearrange, sending plasma and energy back toward Earth. Charged particles are accelerated, currents intensify. Particles enter the upper atmosphere near the polar regions, and the atmosphere begins to glow. That glow is the aurora. Electrons travelling along magnetic field lines collide with oxygen and nitrogen high in the atmosphere. Those atoms and molecules become excited. When they return to lower energy states, they emit light. Different gases and altitudes produce different colours. Green is common. Red can appear during strong events over larger geographic areas. Purple and blue can come from nitrogen emissions. The May 2024 storm pushed visible auroras far beyond their usual high-latitude territory. NASA later described the event as potentially producing one of the most widespread auroral displays in centuries of observation. The aurora is therefore not a decorative extra added to a geomagnetic storm. It is visible evidence that particles and energy are entering Earth's upper atmosphere. Fortunately, most of that interaction occurs far above us. The atmosphere and magnetic field provide excellent protection at ground level. The more practical problems happen because our technology extends into regions where those disturbances matter. Take GPS. A GPS satellite sends an extremely precise radio signal. A receiver on Earth calculates how long that signal has travelled. By comparing signals from several satellites, it determines position. The calculation assumes that the signal's journey through the atmosphere can be corrected accurately. But a geomagnetic storm changes the ionosphere. The amount and distribution of charged material become irregular. Radio signals can be delayed differently from what the receiver expects. For normal navigation, the error may be tolerable. For precision, agriculture, surveying, drilling, aviation, and other applications requiring centimetre-level accuracy, it can become a serious problem. During the May 2024 storm, some high-precision GPS services were disrupted, including systems used in agriculture. NASA's later observations also showed that the event produced two temporary belts of energetic particles around Earth, one of which contained high-energy protons and persisted much longer than researchers expected. Satellites face another problem. A geomagnetic storm deposits energy into Earth's upper atmosphere. The thermosphere heats. As it heats, it expands. At the altitudes occupied by many low Earth orbit satellites, the atmosphere becomes denser. There is still almost no air compared with the surface, but there is enough to create drag. A spacecraft moving around Earth at several kilometers per second notices even a small increase. Its orbit can lose altitude more quickly. Tracking becomes harder because many objects change their trajectories at once. Operators may need additional orbit corrections, and with thousands of satellites now occupying low Earth orbit, the number of objects affected by one strong storm is much larger than it was during earlier solar cycles. Electrical grids experience a different part of the physics. A geomagnetic storm produces changing magnetic fields around Earth. According to electromagnetic induction, a changing magnetic environment can produce electric fields and currents. In the ground and in long-conducting infrastructure, these are known as geomagnetically induced currents. Power transmission networks contain very long conductors. Large transformers are designed primarily to operate with alternating current under normal grid conditions. Geomagnetically induced currents can push transformers into operating states for which they were not designed. They can create extra heating. They can distort current waveforms. They can cause protective equipment to react. In extreme cases, they can contribute to equipment damage or grid instability. This is not hypothetical. In March 1989, a geomagnetic storm contributed to the collapse of the Hydro-Quebec power grid, causing a major blackout. The modern grid is better monitored for space weather hazards, and operators receive warnings from agencies such as NOAA. But the underlying physics has not gone away. A sufficiently powerful geomagnetic disturbance still has the ability to induce currents across large regions. Then there are satellites beyond low Earth orbit. High-energy particles can penetrate spacecraft electronics. They can cause single-event upsets in computers. They can charge materials. Radiation can damage solar panels and instruments over time. Satellites in some orbits pass through Earth's radiation belts, where the particle environment can become much more severe after major storms. The two new temporary belts observed after May 2024 were a reminder that the radiation environment itself can be reorganized in ways scientists are still learning to predict. None of these effects means every G5 storm produces disaster. The May 2024 event did not. Infrastructure operators prepared. Space weather agencies issued alerts. Most satellites continued operating. Electrical grids remained broadly functional. Communication systems experienced disruptions rather than collapse. That distinction is important because discussions of solar storms have a tendency to move from This can affect technology till the sun is about to erase the internet, with very little time spent in between. The realistic concern is more complicated. Modern systems are resilient. They're also interconnected. Navigation depends on satellites. Telecommunications use satellites and ground networks. Financial systems depend on timing. Power grids depend on precise control. Aircraft depend on communication and navigation. Spacecraft depend on reliable electronics, tracking, and orbital predictions. A major geomagnetic storm can put unusual stress on several of these systems at the same time, and the strongest storms are rare enough that we have relatively little modern operational experience with them. May 2024 was valuable, partly because it provided a large amount of real data. NASA said immediately afterward that researchers would be studying the event for years because it offered a chance to test the limits of current storm models. There was another fortunate detail. During the storm, NASA's Stereo A spacecraft happened to be positioned between Earth and the Sun, farther upstream than the usual L1 monitors. Several merged CMEs passed the spacecraft before reaching Earth. Researchers later examined whether Stereo A could have acted as an early warning station. Their analysis found that direct measurements there could have predicted the strength of the resulting storm about 2 hours and 34 minutes earlier than measurements from L1. That is a major improvement over a warning measured in tens of minutes. But notice what had to happen. A spacecraft had to be physically positioned in the path of the disturbance. It had to measure the magnetic field directly. Only then could researchers determine the dangerous orientation with much greater confidence. That is the limitation future space weather systems are trying to overcome. We would like to determine a CME's internal magnetic structure much earlier, ideally close to the Sun. We would like to know how that structure changes while the CME travels. We would like to know whether interactions with the solar wind will rotate it. We would like to know whether one CME will catch another. We would like to know whether the combined magnetic field will remain southward when it reaches Earth. Each of those details changes the storm. Parker Solar Probe provides close measurements of the environment where these structures are developing. Solar Orbiter provides views from different angles and measurements connecting surface magnetism to the heliosphere. Coronagraphs watch CMEs expand away from the Sun. Solar Dynamics Observatory watches active regions evolve. Upstream monitors near Earth provide the final direct measurement before impact. The system is far more capable than it was even 20 years ago, and still, an event like the April 2023 storm can arrive much stronger than expected, because a CME rotated into a more dangerous orientation. That is not a failure to see the eruption. Scientists saw it. It is a failure to know exactly what the eruption would become. Those are different forecasting problems. The same distinction applies to solar cycle 25. Scientists knew the Sun would become more active after minimum. They knew maximum would arrive. They knew flares and CMEs would become more frequent. The surprise was the amount of activity. With individual solar storms, we often know an eruption has happened. The uncertainty lies in its trajectory, magnetic structure, interaction with the solar wind, and final effect at Earth. And those two kinds of uncertainty can overlap. If we underestimate how active the cycle will be, we underestimate the background number of opportunities for significant storms. If we then cannot fully predict the magnetic structure of a particular eruption, we also have uncertainty about the severity of the event itself. That is why solar cycle 25 matters beyond a line on a sunspot chart. It exposed uncertainty at the long end of the forecast. Parker and Solar Orbiter are exposing uncertainty in the physical mechanisms closer to the Sun. Storms such as April 2023 and May 2024 expose uncertainty during the journey to Earth, and the measurement of the most important magnetic field may still arrive only shortly before the disturbance itself, which leaves one uncomfortable question. What happens when the eruption is not merely strong enough to produce extraordinary auroras and temporary disruptions, but belongs to the much rarer class of solar storms our modern technological civilization has never experienced directly? That question is the real reason solar cycle 25 deserves attention. the cycle itself is not the most powerful solar cycle in recorded history. It did not produce a level of sunspot activity that scientists thought was physically impossible. It did not reveal that everything we know about the sun is wrong. What it did was something more useful. It exposed the gap between knowing how the sun generally behaves and being able to predict exactly what it will do. The difference matters. Scientists predicted that solar cycle 25 would happen. They knew it would begin around the minimum following cycle 24. They expected sunspots to increase. They expected the sun's magnetic poles to reverse around maximum. They expected flares and coronal mass ejections to become more frequent. All of that happened. The failure was more specific. The official 2019 prediction expected a relatively modest cycle with a smoothed maximum sunspot number around 115. The actual cycle developed faster and became considerably stronger than that baseline forecast. By October 2023, NOAA had already replaced the static prediction with an updated forecast calling for an earlier and stronger maximum, between 137 and 173. By October 2024, NASA and NOAA were announcing that the Sun had entered its maximum period. NOAA's current solar cycle 25 progression material still describes the original panel prediction as a maximum of 115 and explains that the later forecast was recalibrated using new observations as the cycle unfolded. So the first lesson is not that solar forecasting does not work. It is that forecasting becomes much easier once the thing you are forecasting has already started happening. That sounds obvious, but it matters. Before cycle 25 began, scientists had to predict its strength using information left behind by cycle 24, including the polar magnetic fields. Once cycle 25 had been running for several years, the actual sunspot numbers, radio flux, active region behavior, and rising magnetic activity gave forecasters much more information. The updated forecast improved because the sun had revealed part of the answer. The harder task remains predicting a cycle before that information exists. And solar cycle 25 showed that one of our most trusted clues was not enough. The polar magnetic field before minimum had suggested a cycle broadly similar to cycle 24. That expectation turned out to be too low. There are several possible reasons. Perhaps the field near the poles was not measured as accurately as we thought. The geometry is poor from Earth. The highest latitudes are seen almost sideways. Some regions are difficult to observe directly. Projection corrections and models are needed. Solar Orbiter is only now beginning to provide modern magnetic images from significantly outside the ecliptic. That creates a genuine possibility that better polar observations will improve future forecasts. But it would be premature to blame the cycle 25 error entirely on the instruments. The polar field may have been measured reasonably well. The problem may instead lie in the relationship between that field and what happens next. A precursor can be statistically powerful without being a perfect physical predictor. Solar cycle 25 may have developed through magnetic processes that amplified the following cycle more efficiently than the standard relationship implied. Then there is the dynamo. For decades, many models have placed major importance on the tachocline deep below the convection zone. More recent work has shown that important properties of the solar cycle might emerge from the near-surface shear layer instead. That idea remains under active debate. As of 2026, there is no scientific verdict declaring that the solar dynamo has been moved permanently from the tachocline to the outer few percent of the Sun. Different models continue to investigate contributions from different depths. The relevant lesson is that the location and operation of the Sun's magnetic engine are still not fully settled. That is a substantial thing to admit about an object we have been observing for centuries. We know what powers the Sun. Nuclear fusion in the core. We understand why it shines. We understand its broad internal structure. We understand that plasma motion and differential rotation generate magnetic fields. We know those fields reverse. We know sunspot activity follows a cycle. But knowing those broad facts is not the same as having a complete dynamo model. capable of producing reliable forecasts from first principles. The difference is similar to knowing how hurricanes work and knowing exactly how strong one particular hurricane will be before it forms. Warm ocean water, moist air, rotation, pressure differences. Those principles are understood. The exact storm is harder. On the Sun, the problem is made worse because the engine is hidden inside an opaque sphere of plasma. We cannot directly see the magnetic field throughout the convection zone. We infer internal flows using helioseismology. We measure the field at the surface. Then we build models connecting the two. Any missing process can affect the result. Surface transport added another uncertainty. We tend to describe magnetic flux as moving toward the poles through meridional circulation. That is correct at the broad level. But the real transport is not one constant conveyor belt. The flow changes with latitude. It changes with solar activity. Active regions modify nearby flows. The magnetic flux being transported does not always move exactly like a simple longitudinal average of the plasma. Different depths may contribute differently. The northern and southern hemispheres can behave differently, and the exact active regions supplying the flux are not predictable many years in advance. Their sizes vary, their tilts vary, their latitudes vary. Some emerge with unusual magnetic orientations. A few large regions can make a disproportionate contribution to the future polar field. So even with a perfect dynamo theory, the Sun may contain a degree of practical unpredictability because some of the important magnetic source terms appear in individual active regions only after the cycle is underway. That does not make prediction hopeless. Weather forecasting also contains chaotic processes and still provides enormous value. It means forecasts need uncertainty ranges, continuous observations, and repeated updates. Parker Solar Probe added another piece. Before Parker, much of what we knew about the solar wind came from measurements made far from its source. Parker went inside the corona. It found switchbacks. It found a structured, bursty wind. It crossed an Alphen boundary that was not one clean spherical surface. It linked fast solar wind structure with small-scale magnetic regions and reconnection closer to the Sun. And in April 2026, NASA reported that Parker measurements of a reconnection event had revealed unexpected differences in how protons and heavier ions were accelerated, giving theorists another detail their models need to explain. That does not mean magnetic reconnection is misunderstood in some fundamental sense. Scientists know it happens. They observe it in the solar atmosphere. They observe it in the solar wind. They observe it at Earth. NASA's magnetospheric multiscale mission has flown directly through reconnection regions in Earth's magnetosphere. The open questions are in the detailed behavior. How quickly does reconnection proceed under different conditions? How does it accelerate different particles? How does it trigger or contribute to large eruptions? How does reconnection on small scales combine into events large enough to launch a CME? Those details matter if the goal is prediction. A model can tell us that stressed magnetic fields are capable of erupting. A forecast needs to tell us which active region will erupt and when. That remains extremely difficult. Solar physicists can identify active regions with complex magnetic fields. They can estimate stored magnetic energy. They can watch for changes. They can classify regions according to their magnetic complexity. They can identify conditions associated statistically with strong flares. But an active region can remain complicated for days without producing the eruption people fear. Another can reorganize and flare. There is no reliable equivalent of an alarm clock counting down to magnetic reconnection. That means the first warning of a major flare may simply be the flare. The radiation arrives at Earth 8 minutes later, but we see the event only when that same radiation reaches our instruments. For CMEs, there is more time. Coronagraphs can observe them leaving the Sun. Models can estimate their direction and travel time. That can provide a day or more of warning for the arrival of a major Earth-directed eruption. But, as we saw, knowing that a CME is coming is not the same as knowing exactly how severe the geomagnetic storm will become. One of the key variables is its magnetic orientation. A long-lasting southward magnetic field can drive strong reconnection with Earth's magnetosphere. Remote observations do not yet give forecasters a fully reliable measurement of that internal magnetic field throughout the journey from Sun to Earth. NOAA states plainly that the strength and direction of a CME's magnetic field are critical to storm severity, and that those properties are currently known most directly when the CME reaches upstream monitoring spacecraft. That is perhaps the clearest example of the storm we may not see coming. Not literally unseen, we may see the sunspot, we may see the flare, we may see the CME leaving, we may know that it is moving toward Earth, we may estimate its arrival time, and still, the feature that determines whether the resulting geomagnetic storm is modest or severe may not be measured confidently until the disturbance is relatively close. The April 2023 storm showed how much this can matter. The eruption did not initially look like a severe storm candidate. Later work indicated that interaction with fast solar wind from a coronal hole deflected and rotated the CME. Its magnetic field ended up oriented in a way that transferred much more energy into Earth's magnetosphere than researchers had expected. NASA described the storm as unexpectedly strong, and highlighted the event as a case where understanding CME rotation could improve future forecasts. May 2024 presented a different problem. Several CMEs were launched in quick succession. They bunched together on their way to Earth. The combined disturbance reached G5. Multiple eruptions make forecasting more difficult because they can interact before arrival. A later CME may be moving faster than the one ahead. It can catch it. The structures can compress each other. Their magnetic fields can change. The final disturbance reaching Earth may no longer resemble any one of the original eruptions. Parker Solar Probe has now imaged CME interactions close to the Sun, giving researchers new data on how these disturbances evolve before they enter interplanetary space. But the larger warning comes from events even more extreme than May 2024. In July 2012, the Sun produced an eruption that crossed Earth's orbit. Earth was not there when it passed. NASA's Stereo A spacecraft was. Researchers studying the event concluded that it was exceptionally powerful and comparable in important respects with the famous Carrington event of 1859. Had the eruption occurred about a week earlier, Earth would have been in its path. That event is useful because it removes one comforting assumption. Extreme solar storms are not only events from the 19th century. The Sun produced something extraordinary in the era of smartphones, GPS, commercial satellites, global data networks, and modern power grids. It simply missed us. The 1859 Carrington event occurred before electrical infrastructure looked anything like it does today. Telegraph systems were the advanced communication network of the period. During the geomagnetic disturbance, telegraph equipment produced sparks. Some operators reported that induced currents were strong enough to operate parts of the system even after batteries had been disconnected. Auroras appeared at unusually low latitudes. That storm became the standard historical example of extreme space weather because it was both very strong and directly observed. But it does not represent a known upper limit. There is no law saying the largest possible storm is exactly one Carrington. Nor does the existence of Carrington-level events mean one is expected next Tuesday. Extreme storms are rare. Estimating how rare is difficult because reliable modern measurements cover only a tiny span of solar history. This is another forecasting limitation created by timescale. We have centuries of sunspot observations. We have much shorter records of direct magnetic measurements. The satellite era covers only several solar cycles. And the space weather infrastructure we now care about has existed for an even shorter period. To estimate the frequency of truly extreme events, researchers have to combine modern measurements with historical records and indirect evidence. The most dangerous events are also the ones with the smallest statistical sample. You would like thousands of Carrington-class storms in your database so you could build an excellent forecasting model. Earth would prefer you did not collect them experimentally. So scientists use what nature provides. This is why May 2024 was valuable. It was strong enough to stress modern systems and produce unusual effects without becoming a global catastrophe. Researchers could compare real satellite drag, GPS disturbance, particle populations, auroral boundaries, magnetic measurements, and atmospheric responses with model predictions. The storm even produced 2 temporary radiation belts around Earth, including an unusual proton belt that lasted for months. Every unexpected effect becomes information for the next forecast. The same is true of Solar Cycle 25 itself. A prediction that succeeds tells scientists that the model may be working. A prediction that fails tells them where to look. The cycle says the polar field precursor was not sufficient to capture the final amplitude. Solar Orbiter gives researchers a better view of those poles. The cycle says the dynamo models need to reproduce a stronger outcome from the observed starting conditions. Near-surface dynamo research provides one alternative mechanism to test. The cycle says magnetic transport needs to be represented accurately. Long records from Solar Dynamics Observatory allow scientists to measure how those flows vary. Parker shows that the solar wind and reconnection environment close to the Sun contained structures that were difficult to infer from Earth. Each new observation removes some ignorance. It can also reveal ignorance that was previously hidden. That is normal. Before you measure something directly, a smooth assumption may seem adequate. Once you obtain better data, the smooth line becomes a complicated collection of fluctuations. The scientific model gets harder before it gets better. Space weather forecasting is now moving through exactly that process. One improvement is to measure incoming magnetic fields farther upstream. The usual monitors around L1 may provide only tens of minutes of direct warning before a CME reaches Earth. During the May 2024 storm, Stereo A happened to be farther sunward. A 2025 analysis found that its position could have provided an accurate assessment of the coming storm strength roughly 2 hours and 34 minutes earlier than an L1 monitor. 2.5 hours is not several days, but for some infrastructure decisions it is much better than 20 minutes. Another improvement is to predict the CME's magnetic structure before direct sampling. That requires better knowledge of the magnetic region where the eruption began. It requires understanding reconnection and how the CME forms. It requires knowing its 3-dimensional geometry. Then the model has to propagate that magnetic structure through a changing solar wind. If the CME rotates, the model should capture that. If a coronal hole deflects it, the model should capture that. If 2 CMEs collide, the model should capture that too. None of this is impossible in principle. It is simply difficult. The same progress has already happened in ordinary weather forecasting. Modern forecasts are far better than those of several decades ago because observations, physical models, computing power, and data assimilation improve together. Solar forecasting is following a similar path with a much smaller number of observing stations and an object we cannot surround with weather balloons. Machine learning approaches are also being tested. NASA reported in 2025 on a system called GeoCME that was trained using SOHO images to distinguish CMEs likely to produce geomagnetic storms from those that would not. In one test set, it correctly identified all 21 geo-effective events and 5 of 7 non-geo-effective events. That is promising, but it is not the same as predicting every detail of the resulting storm, and the sample is small enough that broader testing remains important. This distinction should stay with us whenever someone says artificial intelligence will solve solar prediction. It may improve it. So will better physics, so will better observations, so will more spacecraft. The problem is not finding one magic algorithm. The problem is connecting the entire chain from solar interior to technological effect. A useful forecast begins before the sunspot exists. It needs to understand the magnetic cycle that produces the active region. Then it needs to follow the active region as magnetic energy accumulates. It needs to estimate whether reconnection will trigger a flare or CME. It needs to determine the eruption's direction. It needs to reconstruct its magnetic field. It needs to predict how the solar wind will alter that structure. It needs to know how the disturbance will couple to Earth. Then models of the magnetosphere, ionosphere, thermosphere, radiation belts, satellites and power systems have to estimate what those conditions mean for actual technology. That is an extraordinary forecasting chain. A great deal of it already works. The problem is that the most serious outcome may depend on an error at any one of those stages. Solar cycle 25 exposed an error near the beginning. The long-range activity level was underestimated. April 2023 exposed an error in the middle. A CME became more geo-effective because its trajectory and orientation changed. May 2024 demonstrated the difficulty of several eruptions interacting before they reached Earth. Parker showed that the near-Sun solar wind contained structures our simpler models smoothed away. Solar Orbiter showed that the polar regions used in cycle prediction contain detailed magnetic complexity we're only now beginning to observe from a useful angle. Put all of that together, and the important conclusion is not that an enormous storm is secretly on its way. We have no evidence for that, nor is the conclusion that scientists would have no warning. A large Earth-directed CME would very likely be detected, tracked and modelled. Space weather centres would issue alerts. The uncertainty is in exactly how extreme the event would become, and how early we could know that with confidence. A storm could look manageable when it leaves the Sun and become more dangerous because of rotation or interaction during transit. Several eruptions could merge. The critical magnetic field could remain uncertain until upstream monitors sample it. An active region could produce a major eruption after resisting previous attempts to forecast exactly when it would release its energy. Those are real limitations, and modern society has quietly become more exposed to them. There are more satellites, there are more navigation-dependent industries, there are more autonomous systems relying on precise positioning, there are more electrical interconnections, there are astronauts spending long periods in space, with future missions intended to travel beyond low Earth orbit. There are communication systems built around timing, an orbital infrastructure that most people never think about until something stops working. The Sun has not become more dangerous because we invented GPS. We have simply given solar activity more ways to become relevant. That is why the forecasting error of cycle 25 matters. A sunspot prediction does not keep the grid running, but it tells us how mature our understanding of the magnetic cycle has become. And this cycle showed that the answer is not mature enough to stop asking difficult questions. We need better polar measurements. Solar Orbiter is beginning to provide them. We need direct observations close to the source of the solar wind. Parker Solar Probe is providing them. We need better understanding of reconnection. Parker, MMS, and other missions are testing it. We need better models of CME evolution through interplanetary space. Events such as April 2023 and May 2024 give researchers real cases against which those models can be tested. We need better upstream warnings. The accidental position of stereo A during May 2024 showed how valuable additional lead time can be, and we need to keep the uncertainty visible. That may be the least dramatic lesson and the most important one. A forecast should not be treated as a promise. When scientists predicted a weak solar cycle 25, they were not claiming absolute knowledge of the Sun. They were combining the best available measurements and models. The Sun then supplied new evidence. The prediction changed. That is not science breaking. That is science encountering a system more complicated than the model. But there is a practical consequence when the system being modelled can launch magnetized plasma toward a technological civilization. The consequences of being wrong are not limited to correcting a graph. For an ordinary cycle prediction, the correction may arrive over years. For an extreme solar storm, the correction may arrive much faster. A flare can already be affecting the ionosphere when the alert is issued. Energetic particles may follow rapidly. A CME may give us a day or two to prepare. Its most important magnetic orientation may not be known confidently until much later. And if the event belongs to the rare extreme tail of the distribution, we may be trying to judge something we have never measured directly at Earth with modern instruments. That is what Solar Cycle 25 revealed. Not that the sun is completely unpredictable, not that an extreme storm is inevitable, not that the next eruption will shut down modern civilization. It revealed that the chain between solar magnetism and an accurate forecast still contains important gaps. We underestimated the cycle. We are still investigating why. We are only beginning to see the poles properly. We are still debating where important parts of the dynamo operate. We are learning that magnetic transport toward the poles can be more variable than simple models assume. We are finding unexpected structure in the solar wind. We are refining how reconnection accelerates particles. We can watch CMEs leave the sun without always knowing the magnetic field they will deliver to Earth. And somewhere inside all of those uncertainties lies the difference between an impressive aurora and a storm that demands a much more serious response. For now, the sun continues doing what it has done long before satellites, power grids, or human beings existed. Magnetic fields emerge, sunspots form, active regions decay. Flux moves toward the poles, the global field reverses, plasma escapes into the solar wind, some eruptions miss Earth, others arrive. Our part of the process is comparatively new. We are trying to observe enough of that system to know what happens next. Solar Cycle 25 made one thing very clear. We are much better at watching the sun than we used to be. We are not yet as good at predicting it as we would like to think, and the next time a large active region turns toward Earth, the most important question may not be whether scientists can see it. They almost certainly can. The question will be whether the sun has already decided to do something our models have not learned to recognize yet. And that brings us back to the strange position we are in with the sun. We know more about it than any generation before us. We can watch sunspots form in real time, measure magnetic fields across the surface, follow coronal mass ejections as they leave the corona, sample the solar wind with spacecraft, and now even begin looking at the polar regions from angles that were unavailable only a few years ago. And yet Solar Cycle 25 reminded us that observation and prediction are not the same thing. Scientists expected a relatively weak cycle. The sun became considerably more active than the original forecast suggested. The polar fields may not have given us the complete picture. The solar dynamo may work differently from the models we have relied on. Magnetic flux may be transported across the surface in ways that are more variable than a simple model can capture. And even after a major eruption leaves the sun, its magnetic structure can change before it reaches Earth. None of that means we should be afraid of the sun. It means we should keep studying it. Every unexpected solar cycle gives scientists another test. Every spacecraft measurement removes another assumption. Parker Solar Probe is showing us what happens close to the source of the solar wind. Solar Orbiter is giving us a better look at the poles. Future observations will tell us whether those new measurements improve the prediction of the next cycle, and whether we can recognize a dangerous eruption earlier than we can today. So, before we finish, let me ask you one last question. Where are you listening from tonight, and when you see the sun tomorrow, will you think about it a little differently? It may look completely ordinary. No visible explosions, no dramatic warning, just the same bright disk that has been rising over Earth for billions of years. But behind that familiar light is a changing magnetic system that we are still learning to understand. If you enjoyed spending some time with the science tonight, you can leave a like, subscribe to Science for Sleep, and share the video with someone who enjoys learning about the universe without needing the universe to shout about it. And wherever you're listening from, I hope the sun remains quiet above you. Your satellites remain exactly where they should be, your GPS knows where you are, and your electrical grid has a thoroughly uneventful night. Sleep well, and I'll see you next time.